There is a discovery that proved something so fundamental it rewrote our understanding of why anything has weight at all. On July 4, 2012, finding the Higgs boson didn't just confirm another particle, it proved that mass itself comes from invisible interactions happening everywhere, every second, in every atom. The Higgs discovery proved that empty space isn't empty. It proved that a field permeating all existence gives electrons, quarks, and every massive particle their weight through constant interaction. It proved our most ambitious theory about reality was correct, but it also proved something unsettling, that our universe depends on this field maintaining exactly the right strength. Tonight, we trace exactly what this discovery proved about the fabric of reality, from confirming how particles acquire mass to revealing why the weak force behaves differently than electromagnetism. We'll explore the concrete proofs hidden inside those collision patterns and what they mean for our place in the cosmos. We'll begin with the first and most important thing the Higgs proved. Part 1. What happens when the most elegant mathematical theory in physics suddenly predicts that impossible events occur with certainties greater than 100%? In the 1960s, physicists faced exactly this nightmare scenario. Their crown jewel gauge theory demanded that all fundamental force carriers be massless to preserve the underlying symmetries that made the mathematics work. Yet experiments screamed the opposite truth. The W and Z bosons, carriers of the weak nuclear force, possessed enormous masses of 80 and 91 giga-electron volts, respectively. This wasn't merely an inconvenience or a small discrepancy waiting for better measurements. This was a fundamental contradiction that threatened to tear apart the entire theoretical framework of particle physics. Without massless gauge bosons, the probability calculations that governed particle interactions spiraled into mathematical chaos, producing results that violated the most basic principle of probability theory. Imagine a coin flip that comes up heads 40% of the time, and you begin to grasp the absurdity physicists confronted. The weak force responsible for radioactive decay and nuclear fusion in stars simply could not exist as theory described it. Steven Weinberg later called this period the dark ages of particle physics, when the mathematical beauty of gauge theories collided with experimental reality and lost. The contradiction ran deeper than mathematics. If gauge symmetry truly governed nature, then electromagnetic and weak forces should behave identically at high energies. Both should be mediated by massless particles travelling at light speed with infinite range. Yet the weak force operates only across distances smaller than atomic nuclei, suggesting its carriers are incredibly heavy. This created a puzzle that consumed the brightest minds in physics. How could two forces be fundamentally the same yet behave so differently? Murray Gell-Mann described the situation as having two keys that should open the same lock, but one key weighs a feather while the other weighs a boulder. The mathematical formalism of gauge theory represented decades of work by giants like Yang, Mills, and others who had discovered that nature's fundamental forces could be understood as consequences of symmetries. Local gauge invariance wasn't just a mathematical trick, but appeared to be a deep principle organizing all physical interactions. When you rotate a quantum field at every point in space-time independently, the laws of physics remain unchanged. This beautiful idea explained why electric charge is conserved, why forces have their particular forms, and why particles interact in specific patterns. But if the theory demanded massless force carriers and nature provided massive ones, then either the theory was wrong or something was missing from the picture. The crisis deepened when physicists calculated what would happen if they simply inserted mass terms for D and Z bosons by hand. The elegant gauge symmetry shattered. Calculations that should produce finite, sensible answers instead generated infinite nonsense. Richard Feynman spent months attempting to patch the theory, only to conclude that massive gauge bosons and gauge symmetry were fundamentally incompatible. The mathematical machinery that had successfully described electromagnetic interactions for decades simply exploded when applied to the weak force. Worse still, the theory predicted that high-energy scattering processes would violate unitarity, meaning particle collision probabilities would exceed 100%. Nature forbids such violations because they would allow energy to be created from nothing, destroying the conservation laws that underpin all physics. Physicists faced an impossible choice. They could abandon gauge theory, discarding the most beautiful and successful framework ever devised for understanding fundamental forces, or they could ignore experimental evidence that W and Z bosons have mass, pretending that radioactive decay and stellar nucleosynthesis operate according to theoretical prejudice rather than physical reality. Neither option was acceptable. The electromagnetic force had been successfully described by gauge theory for decades. Quantum electrodynamics made predictions accurate to more than 10 decimal places, representing the most precise agreement between theory and experiment in the history of science. Throwing away this success to accommodate the troublesome weak force would be like demolishing a cathedral because the door handle doesn't fit perfectly. Yet the experimental evidence for massive weak bosons was equally undeniable. By the 1960s, careful measurements of radioactive decay rates, neutrino interactions, and nuclear processes all pointed toward the same conclusion. The weak force operates through heavy intermediaries that give it a characteristic short, range and particular strength. CERN's early experiments studying particle collisions provided additional evidence that weak interactions behaved fundamentally differently from electromagnetic ones at low energies, even though theoretical hints suggested they might unify at higher energies. The community split between those who believed gauge theory was fundamentally correct and those who thought it was a beautiful but ultimately flawed approximation. Nobel laureate Sheldon Glashow recalls heated conferences where physicists argued about whether mathematics or measurement should take priority. Some proposed alternative theories that abandoned gauge symmetry entirely. Others suggested that gauge theory applied only to electromagnetism while weak interactions required completely different mathematical treatment. A few radical Wisdom voices proposed that the problem lay not with the theory, but with the assumption that symmetries must always remain unbroken in nature. Could an invisible ocean filling every cubic centimetre of empty space solve the greatest crisis in theoretical physics? In 1964, while most physicists struggled with the mass problem through such increasingly complex mathematical gymnastics, a small group of theorists proposed something so radical it seemed almost mystical. Peter Higgs working alone in Edinburgh, François Englert and Robert Brute collaborating in Brussels, and the trio of Gerald Guralnick, Carl Hagen and Tom Kibble at Imperial College independently arrived at the same extraordinary conclusion. What if the vacuum itself was not empty? What if space throughout the universe contained a field with properties unlike anything previously imagined? This field would possess a crucial characteristic that distinguished it from all other known quantum fields. Instead of having zero energy in its lowest state, it would settle into a configuration where its value everywhere was precisely 246 giga-electron volts. This wasn't just any number pulled from theoretical convenience, but a specific energy density that experiments would later measure with extraordinary precision. The concept challenged every intuition about emptiness and nothingness that humans had developed over millennia of observing the natural world. When we look at apparently vacant regions between stars or inside atomic structures, we see nothing. Yet according to this revolutionary proposal, these regions buzz with constant activity from an omnipresent quantum field oscillating around its non-zero equilibrium value. The Higgs field, as it came to be called, would interact with certain particles but ignore others, giving mass to some while leaving others forever massless. Unlike electric or magnetic fields that can be turned on or off, strengthened or weakened, pointed in different directions or oriented in various configurations, the Higgs field maintains the same strength and orientation throughout all of cosmic history. From the cores of neutron stars to the vast emptiness between galaxies, this field permeates reality with unwavering consistency. Its strength determines not just whether particles have mass, but exactly how much mass they possess through their coupling strength to the field itself. Electrons interact weakly with the Higgs field and therefore have small mass. Top quarks couple strongly and consequently possess enormous mass compared to other fundamental particles. Photons and gluons don't interact with the field at all, remaining forever massless and travelling always at light speed. This mechanism resolved the gauge theory crisis through an elegant mathematical trick called spontaneous symmetry breaking. At extremely high temperatures, like those existing fractions of a second after the Big Bang, the Higgs field would have zero value everywhere. Under these conditions, electromagnetic and weak forces would behave identically, mediated by four massless gauge bosons. All particles would zip around at light speed without any resistance or inertia. But as the universe cooled below a critical temperature of approximately 60 giga-electron volts, the Higgs field would spontaneously develop its non-zero value, fundamentally altering the character of reality. 3 of the 4 massless gauge bosons would acquire mass by absorbing components of the Higgs field, becoming the heavy W and Z bosons we observe today. The 4th would remain massless, becoming the photon. This process preserved the underlying mathematical structure of gauge theory while explaining why electromagnetic and weak forces appear so different at low energies. The beauty of the mechanism lay in its subtlety. Rather than breaking gauge symmetry explicitly, which would destroy the theory's mathematical consistency, the Higgs field hides the symmetry. The fundamental equations retain their elegant gauge invariant form, but the vacuum state in which we live does not respect this symmetry. It's like a perfectly round ball rolling down from the peak of a perfectly symmetric hill. The hill itself remains symmetric, but once the ball settles into a particular valley, the symmetry becomes hidden from everyday observation. The Higgs mechanism made a crucial prediction that would take nearly 50 years to verify experimentally. If this field truly exists, quantum mechanics demands that it must have particle excitations. Just as electromagnetic fields can be excited to produce photons, and electron fields can be excited to produce electrons, the Higgs field must be capable of producing Higgs bosons. These particles would be incredibly massive, roughly 25 times heavier than protons, and would decay almost instantly into other particles. Detecting them would require the most powerful particle accelerator ever built and decades of patient data collection. The theoretical framework also predicted specific relationships between the masses of different particles. The ratio of W boson mass to Z boson mass, the strength of weak interactions compared to electromagnetic ones, and the precise values of coupling constants could all be calculated from the theory's structure. These predictions could be tested experimentally, providing multiple independent checks of whether the Higgs mechanism actually operates in nature. Furthermore, the theory made definite statements about how the Higgs boson itself should behave if discovered. Its spin, parity, decay modes, production rates, and interaction strengths with other particles were all specified by the mathematical framework. Finding a particle with some but not all of these properties would indicate that nature uses a more complex version of the mechanism than the simplest theoretical model. The proposal represented more than just a solution to the gauge theory crisis. It suggested that mass itself was not a fundamental property of particles, but an emergent phenomenon arising from interactions with an underlying field structure. This perspective would revolutionize our understanding of what it means for objects to have weight, inertia, and substance. Rather than being intrinsic characteristics, these familiar properties of matter would arise from dynamic processes occurring at every moment throughout space and time. The Higgs field concept also opened new questions about the nature of vacuum and empty space. If the lowest energy state of the universe contains this omnipresent field, then what we call nothing actually contains enormous amounts of stored energy. The vacuum expectation value of 246 giga-electron-volts represents an energy density pervading all of existence. This energy doesn't usually manifest in observable ways because it represents the baseline condition from which all other physics proceeds. Yet its presence fundamentally shapes the character of reality, determining which particles can exist, how forces operate, and why the universe develops complex structures rather than remaining a bath of massless radiation traveling at light speed forever. What happens when you discover that absolute nothingness contains more energy than a lightning bolt? On July 4, 2012, scientists at CERN announced they had detected the Higgs boson. But the true revelation wasn't just finding another particle. They had proven that empty space itself possesses weight, structure, and an energy density that transforms our understanding of existence itself. The vacuum expectation value of the Higgs field, measured at approximately 246 giga-electron-volts, means that every region of apparently empty space contains energy equivalent to the kinetic power of a speeding freight train compressed into a volume smaller than an atomic nucleus. This discovery shattered the classical notion that vacuum represents true emptiness or absence of substance. Instead, physicists demonstrated that what we perceive as nothing actually constitutes the most energetically dense medium in the universe, filled with invisible quantum fields oscillating at their minimum possible values yet never reaching zero. The measurement represented far more than confirming theoretical predictions about mass generation mechanisms. It revealed that reality itself rests upon a foundation of structured energy that permeates every corner of cosmic space from galactic voids to the interior of solid matter. Before July 2012, the vacuum expectation value remained a theoretical construct, a mathematical necessity required to make gauge theories work properly without experimental verification. Physicists could calculate its approximate magnitude from the measured masses of W and Z bosons, but direct detection of the associated particle remained elusive despite decades of searching with increasingly powerful accelerators. The Large Hadron Collider finally provided sufficient energy and luminosity to create Higgs bosons in controlled conditions, allowing scientists to measure their properties and confirm that the background field actually exists, rather than representing merely a convenient theoretical fiction. When protons collided at energies of 8 trillion electron volts inside CERN's detectors, they occasionally produced the telltale signatures of Higgs boson decay. These events, occurring roughly once in every billion collisions, appeared as characteristic patterns of photons, leptons, and other particles emerging from the collision points. By reconstructing the masses and momenta of these decay products, physicists could work backward to determine that they originated from a particle weighing approximately 125 giga-electron volts, exactly matching theoretical predictions for excitations of the Higgs field above its vacuum state. The discovery process required extraordinary patience and statistical rigor, because Higgs bosons cannot be observed directly. With lifetimes of roughly 10 to the minus 22 seconds, they decay before travelling even a fraction of the distance across an atomic nucleus. What detectors actually record are the daughter particles produced when Higgs bosons disintegrate, creating an experimental challenge analogous to studying dinosaurs by examining only their fossilized footprints. Scientists had to accumulate millions of collision events, searching for subtle excess numbers of particular decay signatures above the background rates expected from all other known processes. The statistical analysis revealed not just that Higgs bosons exist, but that they behave exactly as predicted by the mechanism proposed in the 1960s. Measuring the vacuum expectation value through Higgs boson properties proved that empty space contains a uniform energy density of staggering magnitude. This energy doesn't ordinarily manifest in ways we can directly perceive because it represents the baseline condition from which all physics proceeds. Like fish swimming in water who don't notice the ocean around them, we exist immersed in this energetic medium without sensing its presence through everyday experience. Yet its influence shapes every aspect of material. Reality, determining which particles can exist, how forces operate between them, and why atoms form stable configurations rather than flying apart or collapsing together. The resolution of the mass crisis vindicated decades of theoretical work while opening new frontiers for investigation. By proving that gauge symmetry remains mathematically intact even when particles acquire mass, the Higgs discovery completed the standard model of particle physics, providing the final experimental confirmation that this theoretical framework correctly describes fundamental interactions. The mechanism explains not only why W and Z bosons have mass while photons remain massless, but also why electrons, quarks, and other fermions possess their observed masses through varying coupling strengths to the background field. Perhaps most profoundly, the discovery transformed our philosophical understanding of nothingness and emptiness. Classical physics treated vacuum as the absence of everything, a state of perfect stillness and inactivity where no phenomena occur. Quantum mechanics already suggested that vacuum contains zero-point fluctuations and virtual particle pairs, but these remained somewhat abstract concepts without direct experimental verification. The Higgs field represents something qualitatively different, a classical, macroscopic property of empty space that exists independent of quantum fluctuations. Even if we could somehow eliminate all virtual particles and quantum uncertainties, the Higgs field would persist, maintaining its non-zero value throughout the universe. This realization connects particle physics to cosmological questions about dark energy, vacuum stability, and the ultimate fate of the universe. If space itself contains energy, then the expansion of the cosmos creates new regions filled with Higgs field energy. The relationship between this energy density and the observed acceleration of cosmic expansion remains an active area of research. Additionally, theoretical calculations suggest that our current vacuum state might not represent the absolute minimum energy configuration possible for the Higgs field. If true, our entire universe could eventually tunnel into a lower energy state, fundamentally altering the laws of physics and destroying all existing structures. The Higgs discovery also validated quantum field theory as the correct framework for understanding fundamental particles and their interactions. Every particle, from electrons to photons to the Higgs boson itself, represents an excitation of an underlying field that fills all space. These fields interact with each other through mechanisms that determine particle masses, force strengths, and coupling constants. The successful prediction and detection of the Higgs boson demonstrated that this field-theoretic picture accurately describes reality at its most basic level. Why would a perfectly symmetric universe deliberately choose to destroy its own mathematical elegance? In the primordial cosmos, during the first trillionth of a second after the Big Bang, electromagnetic and weak forces behaved identically. 4 massless gauge bosons mediated interactions between particles that zipped around at light speed without any hint of the mass that would later define their character. The universe existed in a state of perfect electroweak symmetry, where rotating between electromagnetic and weak interactions produced no observable differences. This unified force operated with exquisite mathematical beauty, governed by equations that remained unchanged under transformations between the two seemingly distinct interactions we observe today. Yet, at a precise temperature of 159.5 giga-electron volts, corresponding to energies about 2 trillion times hotter than the Sun's core, something extraordinary occurred that would forever alter the fundamental character of reality. As cosmic expansion cooled the universe below this critical threshold, the Higgs field spontaneously developed a non-zero value throughout all space, breaking the pristine symmetry that had governed the previous epoch. This phase transition represents one of the most important events in cosmic history, fundamentally reshaping how forces operate and particles behave while setting the stage for everything from atomic nuclei to galactic structures that would emerge billions of years later. The process resembles what happens when a pencil balanced perfectly on its tip suddenly falls in a particular direction, choosing one orientation from the infinite possibilities available while the underlying physics remains completely symmetric. Before the transition, the Higgs potential had the shape mathematicians call a Mexican hat, with a central peak surrounded by a circular valley of equal depth. At high temperatures, thermal fluctuations kept the field oscillating around the unstable maximum at 0, maintaining perfect symmetry between all possible orientations. As temperature dropped, these fluctuations weakened until the field could no longer remain balanced at the peak and inevitably rolled down into the surrounding valley. The direction it chose was completely arbitrary, determined by random quantum fluctuations that happened to be slightly larger in one direction than others. Once the field settled into any particular point in the valley, however, the symmetry was irreversibly broken. The field's final resting place became the vacuum expectation value that now permeates all space, giving mass to W and Z bosons while leaving photons massless. This symmetry-breaking mechanism operates through a principle that applies far beyond particle physics. Ferromagnets undergo similar transitions when cooled below their Curie temperature, with magnetic domains spontaneously aligning in particular directions despite the underlying equations being rotationally symmetric. Superconductors develop Cooper pair condensates that break electromagnetic gauge symmetry locally while preserving it, globally. Even crystallization represents spontaneous symmetry breaking, as atoms arrange themselves in specific lattice patterns from initially symmetric liquid configurations. The Higgs transition differs fundamentally from these examples because it affected the entire observable universe simultaneously, establishing the background field configuration that would determine particle masses and force strengths for all subsequent cosmic evolution. Evidence for this ancient phase transition remains embedded in the cosmic microwave background radiation, the oldest light we can observe from roughly 380,000 years after the Big Bang. Although this radiation was emitted long after the electroweak transition, its patterns preserve information about density fluctuations that originated during much earlier epochs. The seeds of cosmic structure visible in CMB temperature variations trace back to quantum fluctuations amplified during cosmic inflation, which occurred very close in time to the electroweak phase transition. Precise measurements by satellites like WMAP and Planck reveal statistical properties of these fluctuations that depend sensitively on the physics operating during the universe's first moments, including the dynamics of phase transitions like electroweak symmetry breaking. The Mexican hat potential that drives this transition has been studied extensively through laboratory experiments at particle accelerators, where high-energy collisions recreate conditions similar to those existing in the early universe. By measuring how the Higgs boson couples to other particles and studying its production rates and decay patterns, physicists can reconstruct the shape of the potential and verify that it indeed has the form required for spontaneous symmetry breaking. These measurements confirm that the field cannot remain stable at zero value and must settle into a non-zero configuration that breaks electroweak symmetry. The potential's curvature determines the Higgs boson mass, while its depth sets the vacuum expectation value that gives mass to other particles. Perhaps most remarkably, theoretical calculations suggest that this symmetry-breaking transition might not represent the final word in cosmic evolution. The measured values of Higgs and top quark masses place our universe very close to the boundary between stability and metastabilort, meaning our current vacuum state might not correspond to the absolute minimum energy configuration possible for the Higgs field. If a lower energy state exists, quantum tunneling could eventually trigger another phase transition that would propagate throughout space at light speed, fundamentally altering the laws of physics and destroying all existing structures. This possibility connects the Higgs discovery to ultimate questions about cosmic destiny and whether our universe will persist indefinitely in its current form. The anthropic implications of spontaneous symmetry breaking are equally profound. The specific value at which the Higgs field settled determines not only particle masses, but also the strength ratios between different forces, the stability of atomic nuclei, and the rates of stellar nuclear fusion. If the field had chosen a significantly different vacuum expectation value, chemistry would be impossible, stars could not shine, and complex structures would never form. The apparent fine-tuning of this value to allow the emergence of complexity and life remains one of the deepest puzzles in fundamental physics, suggesting either extraordinary cosmic coincidence or underlying principles we do not yet comprehend. How does nature perform the ultimate magic trick, making particles vanish completely while simultaneously creating mass from nothingness? When electroweak symmetry breaks spontaneously, the Higgs field develops its non-zero vacuum expectation value, but this process creates a peculiar mathematical puzzle that quantum field theory resolves through one of the most elegant mechanisms ever discovered. According to Goldstone's theorem, whenever a continuous symmetry breaks spontaneously, massless scalar particles called Goldstone bosons must appear, one for each broken symmetry generator. The electroweak symmetry breaking should therefore produce three such massless particles, corresponding to the three generators of the SU2 weak isospin group that become broken when the Higgs field chooses its vacuum state. Yet experiments detect no massless scalar particles beyond the photon, suggesting that something remarkable happens to these would-be Goldstone bosons during the symmetry breaking process. The resolution involves a phenomenon physicists call the Goldstone boson equivalence theorem, where gauge fields in spontaneously broken theories can absorb the degrees of freedom associated with massless scalar excitations. Instead of propagating as independent particles, the three Goldstone bosons become the longitudinal polarization states of the W+, W-, and dibosons, transforming these previously massless gauge fields into massive vector particles. This absorption process explains why we observe exactly three massive weak gauge bosons, rather than four massless ones plus three additional scalar particles. The mathematical machinery behind this transformation reveals the deep connection between symmetry breaking and mass generation that makes the standard model internally consistent. In gauge theories, vector fields naturally possess only two transverse polarization states, corresponding to oscillations perpendicular to their direction of propagation, similar to electromagnetic waves. Massless particles can only exhibit these transverse polarizations because any longitudinal component would require the particle to oscillate parallel to its motion, which is impossible at light speed. When gauge bosons acquire mass through the Higgs mechanism, they gain a third polarization state oriented along their direction of travel, dramatically altering their physical properties and interaction capabilities. The three Goldstone bosons provide exactly the additional degrees of freedom needed to supply these longitudinal polarizations, resulting in massive vector particles with three independent oscillation modes rather than two. The photon escapes this transformation because it corresponds to a linear combination of weak hypercharge and weak isospin that remains unbroken after the Higgs field develops its vacuum expectation value. Electromagnetic symmetry survives the electroweak phase transition, preserving the massless character of its associated gauge boson, while the orthogonal combinations become the massive W and Z fields. This selective symmetry breaking explains why electromagnetic interactions retain their infinite range and universal coupling strength, while weak interactions become short-ranged and appear much weaker at low energies. The surviving Goldstone boson that doesn't get absorbed by gauge fields manifests as the physical Higgs particle detected at CERN, representing the radial excitation mode of the Higgs field around its vacuum expectation value. Direct experimental verification of this mechanism comes from precision measurements of W and Z boson masses and their relationship to other electroweak parameters. The ratio of these masses, approximately 0.88, directly reflects the mixing angle that determines how the original symmetric gauge fields combine to produce the observed massive bosons and massless photon. This ratio can be calculated theoretically from the Higgs mechanism and compared with experimental measurements, providing a stringent test of whether nature actually implements Goldstone boson absorption during symmetry breaking. LEP experiments at CERN measured these mass ratios with extraordinary precision, confirming theoretical predictions to better than 1 part in 1,000 and establishing that the Goldstone mechanism operates exactly as the standard model describes. Furthermore, the coupling strengths between W and Z, bosons and other particles, follow specific patterns predicted by the absorbed Goldstone boson picture, with departures from these patterns providing sensitive probes for physics beyond the standard model. The high-energy behavior of weak interactions also reflects the Goldstone mechanism through the equivalence theorem, which states that longitudinal W and Z bosons behave like the original Goldstone bosons at energies much larger than the weak boson masses. This relationship allows physicists to study electroweak symmetry breaking dynamics by examining high-energy scattering processes involving longitudinal weak-gauge bosons, effectively probing the Goldstone sector directly despite the fact that free Goldstone bosons no longer exist as propagating particles. LHC experiments utilize this connection by studying vector boson scattering processes where W and Z bosons interact with each other, revealing information about the symmetry breaking mechanism through deviations from standard model predictions. The Goldstone mechanism also explains why weak interactions appear so much weaker than electromagnetic interactions at everyday energies despite arising from the same underlying unified force. The masses of W and Z bosons, roughly 80 and 91 Geiger electron volts respectively, act like energy barriers that suppress weak processes at low energies where insufficient energy exists to create these heavy intermediaries virtually. Electromagnetic interactions mediated by massless photons face no such suppression, allowing them to operate efficiently at all energy scales. This difference disappears at energies well above the weak boson masses, where electromagnetic and weak coupling strengths converge toward their unified electroweak value, confirming that these apparently distinct forces represent different manifestations of a single underlying interaction. Temperature-dependent studies of the electroweak phase transition through lattice gauge theory simulations reveal how the Goldstone mechanism emerges dynamically as the universe cools below the critical temperature. Above the transition, thermal fluctuations prevent the Higgs field from developing a stable vacuum expectation value, maintaining exact electroweak symmetry with 4 massless gauge bosons and no physical Higgs particle. As temperature drops through the critical value, the field undergoes a rapid transition to its broken symmetry state, simultaneously generating the vacuum expectation value and triggering the Goldstone absorption process that creates massive W and Z bosons. These simulations provide theoretical support for the cosmological scenario where our universe underwent this transition during its first microsecond, establishing the mass pattern we observe today through a violent phase change that reshaped the fundamental character of space-time itself. What if the most fundamental property of our universe is that it deliberately chose to be lopsided? The Higgs discovery revealed that reality itself is built upon a cosmic act of selection, where the universe picked one particular vacuum state from an infinite spectrum of equally valid possibilities. This choice wasn't guided by any external force or predetermined principle, but emerged from random quantum fluctuations that happened to push the Higgs field slightly more in one direction than others during the electroweak phase transition. The mathematical structure underlying this selection process shows that the Higgs potential possesses perfect rotational symmetry in its abstract internal space, creating a circular valley of degenerate ground states where the field could settle with equal probability anywhere along the rim. Yet our universe exists in a configuration where the field points in one specific direction within this internal symmetry space, breaking the original symmetry completely, despite the underlying equations remaining perfectly symmetric. This asymmetric choice reverberates through every aspect of physical reality, determining particle masses, force strengths, and the very possibility of stable matter formation. The arbitrary nature of this selection cannot be overstated. No physical principle demanded that the Higgs field choose its particular vacuum expectation value rather than any other point in the circular minimum of its potential. The direction was determined purely by chance during the primordial phase transition, when tiny quantum fluctuations amplified by cosmic dynamics happened to favour one orientation over all others. If we could replay cosmic history, the field might settle in a completely different direction, producing a universe with altered particle masses and force relationships while preserving the fundamental mathematical structure of the theory. This randomness connects to profound questions about whether physical laws determine everything about our universe, or whether chance plays an irreducible role in shaping the character of reality itself. The consequences of this arbitrary choice extend far beyond the immediate electroweak sector to influence the entire cosmic inventory of matter and antimatter. During the earliest moments after the Big Bang, the universe contained equal amounts of particles and antiparticles, which should have annihilated completely, leaving behind only massless radiation. Yet we observe a universe dominated by matter, with antimatter existing only in trace quantities or artificial laboratory conditions. This imbalance requires violations of fundamental symmetries that govern particle physics, including charge conjugation parity and time reversal invariance. The Higgs mechanism provides one potential source for such violations through complex phases in the vacuum expectation value that could emerge during the electroweak phase transition, creating conditions where matter and antimatter behave slightly differently. Although the standard model contains insufficient symmetry violation to explain the observed matter-antimatter, asymmetry fully, extensions involving multiple Higgs fields or additional symmetry breaking sectors could amplify these effects during cosmic evolution. The anthropic implications of the Higgs vacuum selection are staggering when we consider how different choices would have affected the development of complexity and structure formation. If the vacuum expectation value had been significantly larger, all fundamental particles would have acquired enormous masses, preventing the formation of lighter elements during the Big Bang nucleosynthesis and making stellar ignition impossible. If the value had been much smaller, particles would remain nearly massless, eliminating the mass hierarchies that allow atomic nuclei to bind together and chemistry to operate through electromagnetic interactions. Even modest changes in the vacuum configuration would alter the delicate balance between electromagnetic and weak force strength that enables nuclear fusion in stellar cores while maintaining atomic stability over cosmic timescales. The fine-tuning required for a life-permitting universe suggests either extraordinary cosmic luck or underlying selection principles that remain hidden from current understanding. Recent theoretical work explores whether the vacuum selection process might be connected to cosmic inflation and the multiverse hypothesis, where different regions of an eternally inflating spacetime could settle into different vacuum configurations. If true, our observable universe would represent just one bubble in an infinite cosmic foam where every possible Higgs vacuum state gets realized somewhere. Anthropic selection would then explain why we observe the particular configuration that allows complex structures to emerge, simply because conscious observers can only exist in regions where the vacuum choice permits their development. This perspective transforms the arbitrary nature of symmetry breaking from a puzzle into a necessary condition for observation itself. The measurement of the Higgs boson mass at 125 giga-electron volts provides crucial information about our vacuum configuration and its stability over cosmic time. Theoretical calculations combining this measurement with the precisely determined top quark mass suggest that our universe exists in a metastable state, rather than the absolute minimum energy configuration possible for the Higgs field. This metastability means that quantum tunneling could eventually trigger a transition to a lower energy vacuum, creating an expanding bubble of altered physics that would destroy all existing structures while propagating throughout space at light speed. The lifetime for such transitions exceeds the current age of the universe by many orders of magnitude, but the possibility introduces fundamental uncertainty about whether our vacuum selection represents a permanent feature of reality or merely a temporary arrangement destined for eventual collapse. Laboratory studies of symmetry breaking in condensed matter systems provide analogies for understanding how vacuum selection operates in particle physics. Liquid crystals undergo phase transitions where molecular orientations spontaneously align in particular directions, breaking rotational symmetry while preserving the underlying molecular physics. Ferromagnetic materials develop magnetization pointing in arbitrary directions below the Curie temperature, creating domains with different orientational choices that reflect the same random selection mechanism operating in the Higgs field. These systems demonstrate that symmetry breaking represents a ubiquitous phenomenon in nature, occurring whenever systems cool below critical temperatures where symmetric configurations become unstable. The universality of this behavior suggests that asymmetric vacuum selection might be inevitable in any sufficiently complex universe, making our lopsided reality a natural consequence of cosmic evolution rather than an extraordinary accident requiring special explanation. What if everything you think you know about why objects have weight is completely backward? The Higgs discovery demolished one of humanity's most fundamental misconceptions about the nature of mass, revealing that this seemingly basic property of matter emerges not from some intrinsic substance within particles, but from dynamic interactions occurring continuously throughout space and time. Before 2012, physicists suspected this revolutionary truth, but the detection of the Higgs boson provided definitive experimental proof that mass represents an acquired characteristic rather than an inherent attribute. Electrons don't contain mass the way marbles contain material. Instead, they generate their inertial properties through constant coupling with the omnipresent Higgs field that permeates every cubic centimeter of cosmic space. This interaction operates like cosmic molasses, where particles moving through the background field experience resistance proportional to their coupling strength, creating the phenomenon we perceive as mass. The strength of each particle's interaction with the Higgs field determines its mass through a relationship so precise that knowing one quantity allows exact calculation of the other. Electrons couple weakly to the field, producing their tiny mass of 0.511 mega-electron volts, while top quarks interact with tremendous strength, resulting in their enormous mass of 173 giga-electron volts. Neutrinos barely couple at all, giving them masses so small that decades of experiments were required to prove they have any mass whatsoever. Photons and gluons don't couple to the Higgs field under any circumstances, maintaining their massless nature and ability to travel at light speed, regardless of energy or frequency. This coupling mechanism operates through what physicists call Yukawa interactions, mathematical terms in the standard model Lagrangian that describe how fermions bind to the scalar Higgs field. These interactions require careful construction to preserve the gauge symmetries that keep the theory mathematically consistent, while allowing particles to acquire mass after spontaneous symmetry breaking occurs. The Yukawa coupling constants represent fundamental parameters of nature that cannot be calculated from first principles, but must be measured experimentally through particle masses and decay rates. Each fermion possesses its own unique coupling strength that remains constant throughout cosmic history, determining not only its mass, but also how strongly it interacts with Higgs bosons during high-energy collisions. The hierarchy of these coupling strengths spans an extraordinary range, from the tiny neutrino couplings near 10 to the -12 to the top quark coupling approaching unity. This enormous variation represents one of the deepest unsolved puzzles in fundamental physics, known as the hierarchy problem, because no known principle explains why nature chose such dramatically different values for particles that otherwise appear quite similar in their quantum properties. Why should the electron couple roughly 300,000 times more weakly than the top quark when both are spin 1/2 fermions with identical electromagnetic charges? The standard model provides no insight into this question, simply accepting the measured coupling values as input parameters without explaining their origin or predicting their relationships. Experimental determination of these coupling strengths requires sophisticated analysis of particle production and decay processes at high-energy accelerators. When Higgs bosons decay into pairs of fermions, the probability for each decay channel depends directly on the square of the relevant Yukawa coupling, allowing physicists to measure these fundamental constants by studying branching ratios and cross-sections. The LHC experiments have successfully observed Higgs decays to tau leptons, bottom quarks, and charm quarks, confirming that the coupling strengths follow the expected pattern where heavier particles interact more strongly with the Higgs field. These measurements provide direct experimental verification that mass generation occurs through the predicted mechanism rather than through alternative theories that might produce similar particle masses through different interactions. The coupling strength determines not just static mass, but also how particles behave during high-energy processes where relativistic effects become important. When electrons or quarks accelerate to speeds approaching light velocity, their effective mass increases according to special relativity. But this enhancement affects only the kinetic energy component while leaving the rest mass unchanged. The rest mass itself emerges entirely from Higgs coupling and remains absolutely constant regardless of motion, energy, or environmental conditions. This distinction between rest mass and relativistic mass clarifies many conceptual confusions about mass-energy equivalence, while emphasizing that fundamental particle masses represent truly universal constants determined by the strength of field interactions rather than properties that vary with circumstances. Theoretical attempts to explain the hierarchy problem have generated numerous extensions of the standard model, including supersymmetry, extra dimensions, composite Higgs models, and anthropic selection mechanisms. Supersymmetric theories predict that every known fermion has a supersymmetric partner with identical Euclid couplings but different spins, potentially providing insights into why the couplings take their observed values through symmetry relationships. Extra-dimensional models suggest that different particles might have varying amounts of their wave functions localized in compact dimensions, leading to suppressed effective couplings for particles confined away from the Higgs field. Composite models propose that the Higgs itself emerges from more fundamental constituents, with Yukawa couplings arising from the internal structure of this composite system. None of these approaches has achieved definitive experimental support, leaving the hierarchy problem as one of the most important open questions driving current theoretical research and experimental programs at the energy frontier. The revolutionary understanding of mass as interaction rather than substance connects to broader questions about the nature of fundamental properties in physics. If mass emerges from field coupling rather than representing an intrinsic characteristic, what other apparently basic features of particles might actually arise from environmental interactions? Charge, spin-in, and other quantum numbers currently appear as given properties of particles, but deeper theories might reveal these attributes as consequences of interactions with additional background fields or geometric structures in higher dimensional spaces. How can the same particle somehow weigh two completely different amounts depending on whether it exists alone or locked inside an atomic nucleus? The proton, one of nature's most familiar building blocks, reveals a startling secret when physicists examine where its mass actually originates. A lone proton weighs approximately 938 mega-electron volts, yet the quarks composing it contribute only about 9 mega-electron volts of Higgs-generated mass, meaning that over 99% of the proton's weight emerges from an entirely different mechanism involving the strong nuclear force and quantum chromodynamics. This revelation transforms our understanding of what gives substance to ordinary matter, showing that the mass making up our bodies, the Earth, and most visible cosmic structures arises primarily from the violent confinement of quarks and gluons, rather than from interactions with the celebrated Higgs field. The two quarks and one down quark inside each proton move at nearly light speed, trapped forever by gluon fields that grow stronger rather than weaker as quarks attempt to separate. Unlike electromagnetic forces that diminish with distance, the strong force exhibits the bizarre property of asymptotic freedom at short ranges, combined with absolute confinement at larger separations. When quarks try to move apart, the energy stored in gluon field lines increases dramatically until it becomes energetically favorable to create new quark-antiquark pairs rather than allowing isolation. This mechanism generates enormous binding energies that manifest as most of the proton's rest mass, through Einstein's mass-energy equivalence relation. The kinetic energy of quarks zipping around inside nuclear particles, combined with the potential energy stored in chromodynamic field configurations, produces the bulk of ordinary matter's inertial properties without requiring any contribution from Higgs field interactions. Lattice quantum chromodynamics calculations performed on supercomputers confirm this picture by solving the strong force equations numerically and reproducing observed hadron masses from first principles. These computations reveal that removing Higgs-generated quark masses entirely would reduce proton and neutron masses by less than 2%, demonstrating that QCD confinement energy dominates the mass budget of composite particles. The calculations also show that gluons themselves, despite being massless like photons, contribute substantially to nucleon masses through their self-interactions and the energy density they create within confined volumes. This QCD mass generation operates through fundamentally different physics than the Higgs mechanism, involving non-perturbative effects where traditional calculational methods break down and require sophisticated numerical techniques to understand. The interplay between these two mass generation mechanisms creates the delicate conditions necessary for atomic stability and chemistry. Higgs-generated masses determine the precise values of fundamental particle properties like electron mass and quark mass ratios, which control nuclear binding energies and electromagnetic fine structure constants. If electron masses were significantly different, atomic orbitals would have altered radii and binding energies, disrupting chemical bonds and making complex molecules impossible. If quark mass ratios deviated from their observed values, nuclear stability would change dramatically, potentially preventing the formation of carbon, oxygen, and other elements essential for biological processes. The QCD contribution provides the bulk mass that gives atoms their substantial character, while Higgs interactions fine-tune the parameters that determine how these atoms interact through electromagnetic force. Even slight modifications to either mechanism would render our universe uninhabitable by destroying the precise balance needed for stable nuclear physics and chemistry. Experimental verification of this dual mass structure comes from deep inelastic scattering experiments where high-energy electrons probe proton internal structure. These measurements reveal how momentum and energy distribute among quarks and gluons, confirming that gluonic contributions dominate the nucleon mass budget. Precision tests of quantum chromodynamics through jet production at particle colliders also validate the theoretical framework describing strong force dynamics and mass generation. The running of the strong coupling constant with energy scale, measured across many orders of magnitude, matches QCD predictions and demonstrates that the same theory governing quark confinement also determines the masses of composite particles formed from quarks and gluons. Further evidence comes from studies of exotic hadrons containing charm and bottom quarks, where the Higgs-generated quark masses become comparable to QCD binding energies, allowing direct observation of how the two mechanisms compete in determining total particle masses. The cosmological implications of dual mass generation extend to stellar nucleosynthesis and galaxy formation processes that depend critically on nuclear masses and binding energies. Big Bang nucleosynthesis calculations show that the primordial abundances of light elements depend sensitively on proton and neutron mass differences, which arise primarily from QCD effects, modified by some small Higgs-generated contributions. Star formation requires gravitational collapse of gas clouds with specific density thresholds determined by the masses of hydrogen and helium atoms, which in turn depend on both nuclear masses and electromagnetic binding energies. Supernova explosions that disperse heavy elements throughout galaxies operate through mechanisms controlled by nuclear physics parameters that emerge from the combined effects of Higgs and QCD mass generation. The remarkable stability of these mass relationships over cosmic time enables the existence of long-lived stars and planets, where complex chemistry can develop over billions of years. Dark matter interactions provide another window into mass generation mechanisms because most proposed dark matter candidates acquire their masses through extensions of the Standard Model that go beyond simple Higgs coupling. Weakly interacting massive particles might obtain their masses through interactions with additional scalar fields, while axions would be nearly massless particles whose tiny masses arise from symmetry breaking in the strong sector. Sterile neutrinos could acquire masses through seesaw mechanisms involving heavy right-handed neutrinos that don't couple directly to the Standard Model Higgs field. Understanding how dark matter obtains its mass could reveal new physics beyond the known mechanisms while providing insights into why the universe contains the observed mixture of visible and dark components. The technological applications of mass generation knowledge include precision metrology and fundamental constants measurements that rely on understanding particle masses at the highest achievable accuracy levels. Atomic clocks based on hyperfine transitions depend on nuclear magnetic moments determined by quark and gluon dynamics within nucleons. Quantum sensors designed to detect new physics often search for tiny variations in particle masses that might signal additional fields or interactions beyond the standard model. Why does nature's most fundamental recipe for mass follow such a perfectly predictable yet mysteriously arbitrary pattern? When CERN's detectors finally captured Higgs bosons decaying into different types of particles, they weren't just observing random nuclear debris, but measuring the precise coupling strengths that determine how strongly each fermion interacts with the field responsible for generating all mass in the universe. The Yukawa coupling constants, those fundamental numbers that connect particle masses to field interactions, emerge from experimental data with startling clarity as physicists analyzed decay channels and production rates across multiple years of collision data. Each decay pathway revealed a different coupling strength, creating a hierarchy that spans more than 12 orders of magnitude from the nearly massless neutrinos to the heavyweight top quark champion. The tau lepton decay channel provided the first direct measurement of fermionic Yukawa couplings when ATLAS and CMS collaborations observed Higgs bosons disintegrating into tau anti-tau pairs. These events, occurring in roughly 6% of all Higgs decays, required sophisticated reconstruction techniques because tau particles themselves decay almost immediately into lighter leptons and neutrinos. By carefully analysing the momentum distributions and missing energy signatures left behind by escaping neutrinos, physicists could determine that the tau Yukawa coupling equals approximately 0.01, precisely matching the value predicted from the tau's measured mass of 1.777 giga-electron volts. This measurement represented a triumph of experimental technique and theoretical understanding, proving that the mass coupling relationship operates exactly as the standard model predicts for third-generation fermions. Bottom quark observations followed several years later when improved analysis methods allowed separation of Higgs decays from the overwhelming background of bottom quark production through other processes. Bottom quarks appear in roughly 58% of all Higgs decays, making them the dominant decay mode, yet their detection requires extraordinary precision because quantum chromodynamics produces bottom quark pairs through numerous competing mechanisms. The measured bottom Yukawa coupling of approximately 0.02 confirmed theoretical expectations while providing crucial tests of the flavor structure within the standard model. These measurements established that the coupling strength correlates directly with particle mass, validating the fundamental assumption that heavier fermions interact more strongly with the Higgs field through proportionality relationships encoded in the theory's mathematical structure. The top quark presents a unique case because its enormous mass of 173 giga-electron volts produces a Yukawa coupling near unity, the maximum possible value consistent with perturbative calculations. Rather than observing top quarks in Higgs decay products, which is kinematically forbidden due to energy conservation, physicists study the reverse process where top quark pairs produce Higgs bosons through virtual interactions. These associated production events occur rarely, but provide direct measurement of the top Yukawa coupling through cross-section calculations that depend sensitively on the coupling strength. The measured value of approximately 0.99 places the top quark tantalizingly close to the unitarity bound where perturbative quantum field theory begins to break down, suggesting that top quarks might play special roles in theories extending beyond the standard model. Precision measurements of the coupling hierarchy reveal patterns that extend beyond simple proportionality to mass. The relationship G between Yukawa coupling and mass follows the exact formula predicted by electroweak theory, where coupling strength equals mass divided by the vacuum expectation value of 246 giga-electron volts. This proportionality holds across 6 orders of magnitude in mass, from the electron at 0.501 mega-electron volts to the top quark at 13 giga-electron volts, providing remarkable confirmation that a single mechanism generates all fermion masses through varying interaction strengths. The mathematical precision of this relationship eliminates alternative explanations for mass generation while establishing the Higgs field as the universal source of inertial properties for all fundamental matter particles. Experimental verification of these coupling measurements requires extraordinary statistical precision because Higgs boson production rates are intrinsically low and backgrounds from other processes can mimic the desired signals. The LHC produces roughly 1 Higgs boson per billion proton collisions, and each specific decay channel occurs with branching ratios determined by the relevant coupling strengths. Detecting tau decays requires identifying the complex cascade patterns produced when tau particles themselves decay. While bottom quark measurements demand sophisticated algorithms to distinguish Higgs-produced pairs from the copious background of bottom quarks created through strong interactions, top quark-associated production involves reconstructing the complete final state from multiple high-energy jets and leptons, requiring advanced machine learning techniques to extract signal events from overwhelming backgrounds. The success of these measurements demonstrates both the power of modern experimental methods and the precision of theoretical predictions based on the Higgs mechanism. Future measurements aim to extend coupling determinations to second-generation fermions, including muons and charm quarks, where the smaller masses produce correspondingly weaker couplings that challenge current experimental sensitivities. The muon-Yukawa coupling, GIM, predicted to be approximately 0.006, lies barely within reach of high-luminosity LHD capabilities, while charm quark couplings require novel analysis strategies to overcome backgrounds from other charm production mechanisms. First-generation fermions like electrons and up quarks have couplings so small that direct measurement appears impossible with foreseeable technology, though indirect constraints from precision electroweak measurements and flavor-changing neutral current searches provide upper limits consistent with standard model expectations. The coupling hierarchy also connects to fundamental questions about why nature chose these particular values rather than others. No known principle explains why electron, muon, and tau masses follow their observed pattern, or why quark masses span such enormous ranges while maintaining specific ratios that allow nuclear stability and stellar nucleosynthesis. The measured Yukawa couplings simply parameterize these mass relationships without providing deeper understanding of their origins, leaving the flavor puzzle as one of the most important unsolved problems in particle physics that future theories must address through new symmetries, dynamics, or environmental selection mechanisms. What if everything we think of as solid, tangible reality is actually composed of invisible waves rippling through omnipresent fields that fill every corner of space? The Higgs discovery provided the most compelling evidence ever gathered that quantum field theory represents the true foundation of physical reality, demonstrating that what we perceive as particles are merely localized excitations of underlying field structures that permeate the entire universe. Before July 2012, this field-based picture remained largely theoretical, supported by mathematical elegance and indirect experimental hints, but lacking definitive proof that fields themselves could be directly detected and measured. The observation of Higgs bosons changed everything by confirming that particles represent temporary disturbances in permanent field configurations, rather than fundamental building blocks moving through empty space. This revelation validated decades of theoretical development, while fundamentally altering our conceptual understanding of what constitutes the basic ingredients of nature. The Higgs field differs crucially from all previously known quantum fields because it maintains a non-zero value throughout space, even in the absence of particles, providing direct experimental access to the field itself rather than just its excitations. Electromagnetic fields can be reduced to zero by removing all photons and charges, while electron fields reach their vacuum state when no electrons are present, but the Higgs field necessarily maintains its 246 giga-electron-volt vacuum expectation value everywhere and always. This omnipresence makes the Higgs field uniquely observable through its background effects on particle masses and interactions, offering the first opportunity to study a quantum field as a macroscopic physical medium rather than merely through its particulate manifestations. The detection of Higgs bosons represents waves propagating through this background field, analogous to sound waves travelling through air or water waves moving across ocean surfaces. Just as studying ripples reveals properties of the underlying medium, analysing Higgs boson properties illuminates characteristics of the field that generates all mass in the universe. Perhaps most significantly, the Higgs boson represents the first and only scalar field particle ever detected in nature, possessing zero intrinsic angular momentum and no preferred spatial orientation. All other known fundamental particles carry spin angular, momentum that determines how they behave under rotational transformations, with fermions having half-integer spins and gauge bosons having integer spins that reflect their roles as matter constituents and force carriers respectively. The scalar nature of the Higgs field allows it to fill space uniformly, without creating preferred directions or violating rotational symmetry, enabling it to serve as the universal background medium that gives mass to other particles through isotropic interactions. This unique spin-zero character validates theoretical predictions about how mass generation must operate while distinguishing the Higgs mechanism from alternative proposals that would require vector or tensor fields with more complex transformation properties. The field-theoretic interpretation gains additional support from precision measurements of Higgs boson production and decay rates that match quantum field theory calculations with remarkable accuracy. These processes involve virtual particle exchanges and quantum loop corrections that exist only within the field-based framework, having no meaningful interpretation in particle-based descriptions of fundamental physics. When physicists calculate Higgs production through gluon fusion, the dominant mechanism at the Large Hadron Collider, the theoretical predictions require summing contributions from virtual top quark loops that mediate interactions between gluons and the scalar field. These loop effects produce measurable consequences for production cross-sections and kinematic distributions that have been verified experimentally, providing direct evidence that virtual processes predicted by quantum field theory actually occur in nature. Similarly, the rare decay of Higgs bosons into pairs of photons proceeds entirely through virtual W boson and top quark loops, since the electrically neutral Higgs field cannot couple directly to photons. The observed branching ratio for this decay channel matches field-theoretic calculations to within experimental uncertainties, confirming that virtual particle exchanges have real physical consequences measurable in laboratory experiments. The validation of quantum field theory through Higgs physics extends beyond the standard model to encompass the entire conceptual framework underlying modern particle physics and cosmology. Every successful prediction of particle masses, interaction rates, and symmetry patterns relies fundamentally on field-theoretic calculations that treat particles as excitations of underlying fields. The electromagnetic field gives rise to photons, the electron field produces electrons and positrons, quark fields generate the constituents of protons and neutrons, and gauge fields mediate the fundamental forces through their boson excitations. The Higgs discovery confirms this comprehensive picture by demonstrating that even mass generation operates through field interactions rather than through intrinsic particle properties, completing the transition from particle-based to field-based descriptions of fundamental physics that began with the development of quantum electrodynamics in the 1940s. Modern cosmology also depends critically on quantum field theory for understanding the early universe, cosmic inflation, and dark matter interactions that shape large-scale structure formation. The same mathematical framework that describes Higgs physics governs inflationary dynamics through scalar field evolution in curved spacetime, connects particle physics to gravitational phenomena through field-theoretic approaches to quantum gravity, and provides theoretical foundations for understanding how quantum fluctuations in primordial fields generate the density perturbations observed in the cosmic microwave background. The experimental confirmation that fields represent fundamental reality rather than mathematical abstractions therefore supports not only particle physics, but the entire modern understanding of cosmic evolution from quantum origins to macroscopic structures. Future developments in quantum field theory may reveal additional field types beyond those included in the standard model, potentially explaining dark matter through new scalar or vector fields, accounting for neutrino masses through sterile neutrino fields, or describing quantum gravity through emergent field dynamics at the Planck scale. The Higgs discovery established the experimental methods and theoretical frameworks needed to search for such extensions while providing confidence that field-based approaches will continue to illuminate the deepest layers of physical reality. How can a particle that refuses to interact directly with light somehow decay into pure photons with measurable probability? The Higgs boson's decay into two photons represents one of the most striking confirmations that virtual quantum process, those ghostly intermediate states that exist only in mathematical calculations, possess genuine physical reality with observable consequences. This decay channel should be absolutely forbidden by conservation laws, since the electrically neutral Higgs field carries no electromagnetic charge and therefore cannot couple directly to photons under any circumstances. Yet experiments detect this decay occurring in roughly 0.2% of all Higgs disintegrations, providing irrefutable evidence that quantum mechanics operates through mechanisms far more subtle and counterintuitive than classical physics could ever accommodate. The resolution requires understanding how virtual particle loops mediate interactions between fields that cannot communicate directly, creating effective couplings through intermediate states that never appear as real particles in the final products. When a Higgs boson decays into photons, the process proceeds entirely through virtual W bosons and top quarks that form closed loops connecting the scalar field to electromagnetic radiation. These virtual particles exist only momentarily within the quantum uncertainty allowed by the energy-time uncertainty principle, borrowing energy from the vacuum to facilitate interactions before disappearing without violating conservation laws. The W boson loops dominate this process because of their strong coupling to both the Higgs field and electromagnetic interactions, while top quark contributions arise from their enormous Yukawa coupling that makes them the most strongly interacting fermions with the Higgs mechanism. Calculating the decay rate requires sophisticated quantum field theory techniques that sum contributions from all possible virtual particle configurations, demonstrating that apparently empty space teems with fluctuating fields and transient particle-antiparticle pairs that influence observable phenomena. The mathematical framework behind these virtual processes reveals quantum field theory's most profound insight, that vacuum itself represents an active medium filled with zero-point fluctuations and virtual particle exchanges rather than passive emptiness. Every point in space continuously spawns virtual particles that exist for brief intervals determined by quantum uncertainty before annihilating back into the vacuum. These fluctuations normally cancel out and produce no measurable effects, but when real particles interact, they can tap into this virtual activity to enable processes that would be impossible in purely classical physics. The Higgs photon coupling emerges from virtual W bosons that couple strongly to both the Higgs field through the mass generation mechanism and to photons through their electric charge, creating an effective interaction between the neutral scalar field and electromagnetic radiation mediated entirely by charged intermediaries. Experimental verification of this quantum loop mechanism comes from precise measurements of the two-photon decay branching ratio and its dependence on Higgs boson kinematics. The observed rate matches theoretical predictions that include contributions from virtual W bosons, top quarks, and other charged particles with extraordinary accuracy, confirming that quantum corrections calculated through loop diagrams correspond to real physical processes occurring in nature. Additional evidence emerges from studying how the decay rate varies with the Higgs boson's momentum and environment, since virtual particle effects depend sensitively on the energy scales and field configurations present during the decay process. These measurements provide direct tests of quantum field theory's most abstract predictions, while demonstrating that virtual processes have concrete experimental consequences rather than representing mere mathematical conveniences. The success of these calculations validates the entire perturbative expansion that underlies modern particle physics, where physical processes are computed as a series of increasingly complex virtual particle exchanges that converge to finite measurable results. Beyond confirming quantum mechanics, the virtual process interpretation connects Higgs physics to broader questions about vacuum structure and the fundamental nature of empty space. If virtual particles can mediate interactions between otherwise non-interacting fields, then vacuum fluctuations must possess genuine physical reality rather than representing artifacts of theoretical formalism. This perspective has profound implications for understanding phenomena ranging from the Casimir effect, where virtual photons create measurable forces between conducting plates, to Hawking radiation from black holes, where virtual particles near event horizons become real through gravitational effects. The vacuum energy density associated with quantum fluctuations also relates to cosmological problems like dark energy and the cosmological constant, suggesting that understanding virtual processes in particle physics might illuminate the largest scale dynamics governing cosmic acceleration and expansion. Laboratory studies of quantum corrections in Higgs physics therefore provide windows into fundamental questions about space-time structure and vacuum properties that extend far beyond the Standard Model. Future precision measurements of virtual loop effects in Higgs production and decay will test quantum field theory at unprecedented levels of accuracy, while searching for deviations that might signal new physics beyond the Standard Model. Extensions of the theory involving supersymmetry, extra dimensions, or composite Higgs models predict specific modifications to virtual particle contributions that would alter decay rates and production cross-sections in characteristic ways. By measuring these quantum corrections with increasing precision, physicists can probe energy scales far above those directly accessible through particle production, using virtual processes as sensitive indicators of new phenomena that might exist at the Planck scale or other fundamental thresholds. The discovery that virtual quantum loops have measurable consequences therefore opens new frontiers for exploring the deepest layers of physical reality through precision tests of processes that exist only in the shadowy realm between possibility and actuality. How can mathematical equations written decades before experimental verification predict the behavior of subatomic particles with accuracy that exceeds 1 part in 1,000? The Higgs discovery represents far more than detecting another fundamental particle. It validates the entire mathematical architecture underlying modern physics through measurements that confirm theoretical predictions with breathtaking precision across multiple independent observables. When ATLAS and CMS collaborations measured Higgs boson production cross-sections, decay branching ratios, and kinematic distributions, they found agreement with standard model calculations that borders on the miraculous, demonstrating that gauge theory captures something profound about the mathematical language nature uses to organize fundamental interactions. The production cross-section for gluon fusion, the dominant mechanism creating Higgs bosons at the Large Hadron Collider, matches quantum chromodynamics calculations that incorporate next to leading order corrections with uncertainties below 10%. This agreement validates not only the specific prediction, but the entire perturbative framework that treats strong interactions as expansions in the coupling constant, confirming that quantum field theory correctly describes how quarks and gluons behave inside colliding protons, even under extreme conditions where energies reach several trillion electron volts. The mathematical machinery underlying these calculations involves summing infinite series of increasingly complex virtual particle exchanges, a procedure that should fail catastrophically if gauge theory misrepresented the fundamental structure of reality. Vector boson fusion represents another crucial production mechanism where theoretical predictions face stringent experimental tests through measurements of forward jet tagging and central rapidity gaps that characterize electro-weak interactions. The observed rates and kinematic patterns match calculations based on the SU2 times U1 gauge structure of electro-weak theory, providing independent confirmation that the mathematical symmetries postulated by Weinberg and Salem actually govern weak nuclear processes in nature. Associated production with W or Z bosons offers additional verification through measurements of invariant mass distributions and angular correlations that depend sensitively on the gauge couplings and Higgs field interactions encoded in the standard model Lagrangian. Each production mode tests different aspects of the theoretical framework, while contributing to a comprehensive picture where mathematical predictions consistently align with experimental observations across energy scales, particle multiplicities, and detector acceptances. Decay branching ratios provide equally compelling evidence for the mathematical foundations of particle physics through measurements that span 4 orders of magnitude in probability. The dominant decay into bottom quark pairs occurs with a branching fraction of approximately 58%, precisely matching calculations based on the bottom quark Yukawa coupling and QCD corrections that modify the basic tree-level process. Decays to do boson pairs and Z boson pairs follow the patterns expected from gauge boson masses and couplings, while the rare decay to 2 photons proceeds through virtual loops with rates determined by the electromagnetic charges and masses of all particles contributing to the quantum corrections. The tau-lepton decay channel confirms fermionic Yukawa interactions, while providing tests of lepton universality and flavor conservation that constrain extensions beyond the standard model. Even the Higgs boson mass itself, measured at approximately 125 giga-electron volts, falls within the range predicted by global fits to electroweak precision data collected over decades of experiments, demonstrating remarkable consistency between direct detection and indirect constraints derived from quantum loop effects. The mathematical success extends beyond individual measurements to encompass the entire web of relationships connecting different observables through gauge invariance and symmetry principles. Custodial symmetry ensures that the ratio of W and Z boson masses remains close to unity after electroweak symmetry breaking, a prediction confirmed by precision measurements at the Large Electron-Positron Collider and validated again through Higgs coupling determinations. The oblique parameters ST and U that characterize deviations from standard model predictions through new physics contributions all remain consistent with 0 within experimental uncertainties, indicating that no significant corrections to the gauge structure appear at currently accessible energy scales. Running coupling constants measured across multiple experiments exhibit the energy dependence predicted by renormalization group equations, confirming that gauge theories correctly describe how interaction strengths evolve with momentum transfer. These relationships form an interconnected network where each measurement constrains others through theoretical connections, creating over-constrained systems that would reveal inconsistencies immediately if the underlying mathematics were incorrect. Perhaps most profoundly, the mathematical vindication demonstrates that nature operates according to principles of gauge invariance and local symmetry that seemed abstract and artificial when first proposed by Yang and Mills in the 1950s. The requirement that physics remain unchanged under local transformations of quantum fields initially appeared to be a mathematical curiosity with little connection to experimental reality, yet this principle now underlies every successful theory of fundamental interactions. Electromagnetic interactions arise from U1, gauge symmetry, weak interactions from SU2, symmetry, strong interactions from SU3, symmetry, and the Higgs mechanism from the spontaneous breaking of the combined SU2 times U1, electro-weak symmetry. The mathematical elegance of these gauge theories, with their automatic incorporation of conservation laws and renormalizability properties of Dubois, suggested to theorists that they might represent more than computational conveniences, and the Higgs discovery confirms this intuition by showing that gauge symmetry truly governs the fundamental architecture of reality. The implications extend beyond particle physics to encompass our understanding of how mathematics relates to physical truth, suggesting that certain mathematical structures possess a reality and necessity that transcends their human origins as abstract symbolic systems. What if the electromagnetic force that powers every electronic device and the weak nuclear force that drives radioactive decay are actually the same fundamental interaction masquerading as separate phenomena? The Higgs discovery provided definitive proof that these apparently distinct forces represent different manifestations of a single unified electroweak interaction, validating one of the most elegant theoretical achievements in modern physics, while demonstrating that nature's economy extends to its most basic organizational principles. Before electroweak symmetry breaking occurred, in the primordial universe, electromagnetic and weak interactions behaved identically, mediated by four massless gauge bosons that carried equal coupling strengths and infinite ranges. The subsequent phase transition that gave the Higgs field its vacuum expectation value transformed three of these bosons into the massive W+, D- and Z particles, while leaving the fourth as the massless photon, creating the illusion that two fundamentally different forces operate in our low-energy world. This unification represents far more than mathematical convenience. It reveals that nature organizes its fundamental interactions according to deeper symmetry principles that become manifest only under extreme conditions or through sophisticated theoretical analysis. The measured masses of W and Z bosons provide the most direct evidence for electroweak unification through their precise relationship to the weak mixing angle, a fundamental parameter that determines how the original symmetric gauge of fields combine to produce the observed massive and massless states. The W boson mass of approximately 80.4 giga-electron volts and Z boson mass of roughly 91.2 giga-electron volts yield a mass ratio of 0.881, which matches the theoretical prediction code θW, where θW represents the Weinberg angle that characterizes the mixing between weak isospin and hypercharged symmetries. This relationship cannot be derived from treating electromagnetic and weak forces as independent interactions, but emerges naturally from the electroweak unification framework, providing compelling evidence that a single gauge theory underlies both phenomena. The precision of this agreement, measured to better than 0.1% accuracy through decades of careful experiments at multiple facilities, leaves no doubt that the unification represents physical reality rather than theoretical speculation. LEP experiments at CERN provided crucial validation of electroweak unification through precision measurements of Z boson properties that tested the theory's predictions at the quantum loop level, where virtual particle effects become significant. The Z resonance studies revealed that the weak mixing angle runs with energy according to renormalization group equations, exhibiting the logarithmic variation predicted by quantum field theory as virtual particle contributions modify the effective coupling strengths. These running coupling measurements demonstrate that electromagnetic and weak interactions converge toward equal strengths at high energies while diverging at low energies due to symmetry breaking effects, exactly as expected if they represent different aspects of a unified electroweak force. Additional confirmation comes from measurements of neutral current processes mediated by boson exchange, which exhibit the characteristic interference patterns between electromagnetic and weak amplitudes that arise only in unified theories where both interactions spring from the same underlying symmetry structure. The impossibility of electroweak unification without the Higgs mechanism becomes clear when examining the mathematical requirements for combining electromagnetic and weak interactions into a single gauge theory. Electromagnetic interactions must remain massless to preserve their infinite range and universal coupling to electric charge, while weak interactions require massive carriers to explain their short range and apparent weakness at low energies. Standard gauge theory cannot accommodate this mixed pattern without violating fundamental principles like gauge invariance and renormalizability that ensure mathematical consistency and finite calculational results. The Higgs mechanism resolves this contradiction by allowing gauge bosons to acquire mass through spontaneous symmetry breaking while preserving the underlying gauge structure, enabling theorists to construct unified models that remain mathematically well-behaved. Without the Higgs field, any attempt to insert mass terms for weak gauge bosons by hand destroys the gauge symmetry and produces infinite results in quantum calculations, making the theory useless for predictions. The electroweak unification also connects to grand unified theories that attempt to incorporate the strong nuclear force into an even more comprehensive framework operating at energy scales near 10 to the 16 giga-electron volts. The measured values of electromagnetic, weak and strong coupling constants exhibit a pattern of convergence when extrapolated to these extreme energies, suggesting that all three forces might unify into a single interaction at temperatures existing only during the first instance after the Big Bang. Supersymmetric extensions of the Standard Model improve this convergence significantly, providing theoretical motivation for searching for supersymmetric particles that might appear at LHC energies. The successful unification of electromagnetic and weak forces therefore serves as a prototype for understanding how apparently disparate phenomena might reflect deeper underlying unities that become apparent only through theoretical insight and experimental verification. Cosmological implications of electroweak unification extend to baryogenesis mechanisms that might explain why the universe contains more matter than antimatter, since the unified electroweak theory contains CP-violating phases that could generate matter, antimatter, asymmetries during the phase transition epoch. The unification also affects Big Bang nucleosynthesis calculations that determine primordial light element abundances, since weak interaction rates during the first few minutes of cosmic evolution depend on the unified electroweak parameters rather than on separate electromagnetic and weak couplings. Dark matter detection experiments rely on electroweak unification when calculating interaction rates for hypothetical weakly interacting massive particles, while neutrino astronomy depends on unified theory predictions for neutrino production and propagation through cosmic media. What determines the precise numerical relationship that governs how nature distributes strength between the fundamental forces, and why does this distribution follow such an exact mathematical pattern? The Weinberg angle, represented by the symbol θw, stands as one of the most precisely measured quantities in all of physics, yet its value of approximately 28.7 degrees emerges from the deepest mysteries surrounding why universal constants take their observed values rather than any of the infinite alternatives that mathematics permits. This angle determines how the original electroweak gauge fields mix to produce the massive W and Z bosons, along with the massless photon, establishing the relative strengths of electromagnetic and weak interactions through a relationship so fundamental that altering it even slightly would render our universe unrecognizable. The sinus squared of the Weinberg angle, measured to be approximately 0.231, connects directly to the ratio of gauge coupling constants that characterize electromagnetic and weak interactions before symmetry breaking occurs, providing a window into the unified electroweak theory that operated during the universe's first microsecond. The precision with which this value has been determined through multiple independent experimental techniques demonstrates that it represents a genuine universal constant rather than an accident of measurement or theoretical approximation. Experiments spanning decades have measured sin² theta W through Z, boson decays at LEP, neutral current neutrino scattering at various facilities, atomic parity violation in cesium atoms, and deep inelastic scattering processes, all yielding results that agree within tiny error bars and confirm the theoretical framework connecting electroweak unification to observable phenomena. The consistency of these measurements across vastly different energy scales and experimental environments proves that the Weinberg angle truly characterizes a fundamental aspect of nature's architecture, rather than merely describing low-energy effective behavior that might change under different conditions. The mathematical relationship between the Weinberg angle and the Higgs field reveals how the vacuum expectation value of 246 giga-electron volts determines not just particle masses, but the entire hierarchy of force strengths that governs atomic physics, nuclear processes, and stellar evolution. When the Higgs field develops its non-zero value during electroweak symmetry breaking, it simultaneously fixes the mass ratio between W and Z bosons and determines how strongly these particles couple to electromagnetic currents versus weak nuclear processes. The W boson mass equals the Z boson mass times the cosine of the Weinberg angle, while the electromagnetic coupling constant relates to the weak coupling through the sine of the same angle, creating an interconnected web of relationships that would be impossible to achieve through coincidence. These connections demonstrate that the Higgs mechanism does far more than generate mass. It establishes the fundamental parameter structure that makes complex chemistry and nuclear physics possible by ensuring that electromagnetic forces remain strong enough to bind atoms while weak forces stay weak enough to allow stable nuclei and controlled stellar burning. The mysterious aspect of the Weinberg angle lies not in its precise measurement, but in the complete absence of any theoretical principle that explains why nature chose this particular value from the continuum of possibilities. Grand unified theories attempt to relate the Weinberg angle to other coupling constants through symmetry relationships that operate at extremely high energies, but these models require additional assumptions about symmetry breaking patterns and particle content that cannot be verified experimentally. String theory approaches suggest that the angle might be determined by the geometry of compactified extra dimensions, with different compactification schemes producing different mixing angles, but no definitive calculations have emerged that predict the observed value from first principles. Anthropic arguments propose that conscious observers can exist only in universes where the Weinberg angle falls within a narrow range that permits stable atoms and long-lived stars. But this perspective raises more questions than it answers about the nature of physical law and the role of observation in determining fundamental parameters. The connection between the Weinberg angle and other dimensionless constants in physics hints at deeper organizational principles that remain hidden from current understanding. The fine structure constant that characterizes electromagnetic interaction. Strength, the strong coupling constant that governs quantum chromodynamics, and the various mass ratios between fundamental particles all appear to be independent parameters that could take any values consistent with mathematical consistency. Yet their measured values seem remarkably well tuned to permit the emergence of complexity, with small changes in any one constant potentially destroying the delicate balance needed for nuclear stability, stellar nucleosynthesis, and chemical diversity. The Weinberg angle participates in this apparent fine-tuning through its role in determining weak interaction rates that affect Big Bang nucleosynthesis, stellar evolution, and neutrino propagation through cosmic media. Future precision measurements of the Weinberg angle will test whether it truly remains constant across cosmic time and under extreme conditions that might reveal new physics beyond the standard model. Experiments at the high luminosity LHC will measure electroweak parameters with unprecedented accuracy, searching for tiny deviations that might signal additional gauge groups, extra dimensions, or supersymmetric particles that could explain why the fundamental constants take their observed values. Neutrino experiments will probe the Weinberg angle at different energy scales through oscillation phenomena and interaction cross-sections, while atomic physics measurements will test whether electromagnetic and weak couplings maintain their precise relationship under varying environmental conditions. The mystery of why the Weinberg angle equals 28.7 degrees rather than some other value represents one of the deepest unsolved problems in theoretical physics, challenging our understanding of whether physical laws are inevitable consequences of mathematical logic or contingent features of our particular cosmic environment? Could the successful marriage of electromagnetic and weak forces represent merely the first step toward an even grander unification that encompasses all fundamental interactions within a single theoretical framework? The electro-weak unification achieved through the Higgs mechanism provides compelling evidence that nature operates according to unified principles at high energies, suggesting that the strong nuclear force might also merge with electro-weak interactions under sufficiently extreme conditions to create a grand unified theory encompassing 3 of the 4 known forces. When physicists extrapolate the measured coupling constants of electromagnetic, weak, and strong interactions to higher and higher energies using renormalization group equations, these apparently different force strengths exhibit a remarkable tendency to converge toward a common value at energy scales around 10 to the 16 giga-electron volts, roughly 1 trillion times more energetic than anything achievable with current accelerators. This convergence cannot be mere coincidence because the 3 coupling constants evolve independently according to the particle content and symmetry structure of each interaction, yet their trajectories intersect at nearly the same point when projected to grand unification energies. The mathematical framework describing this convergence treats the 3 forces as different components of a single gauge theory based on larger symmetry groups like SU5 or SO10 that contain the standard model gauge group as a subgroup, analogous to how electroweak theory contains electromagnetic and weak interactions within its SU2 times U1 structure. These grand unified theories predict that protons should decay with extremely long lifetimes determined by the unification scale, a process that has been searched for extensively but never observed despite decades of underground detector experiments. The non-observation of proton decay provides important constraints on grand unification models, while leaving open the possibility that more sophisticated versions of the theory might avoid this prediction through alternative symmetry breaking patterns. Supersymmetric extensions of the standard model dramatically improve the coupling constant convergence by introducing additional particles that modify the renormalization group running and bring the 3 trajectories to a precise intersection point. Supersymmetry proposes that every known fermion has a bosonic partner and every known boson has a fermionic partner, effectively doubling the particle spectrum while preserving many of the mathematical relationships that make the standard model successful. The supersymmetric particles would have masses determined by the scale of supersymmetry breaking, which could range from hundreds of giga-electron volts accessible to the LHC up to the grand unification scale itself. Searches for supersymmetric particles at CERN have so far yielded negative results, pushing the supersymmetry breaking scale to higher energies and making the theory less natural as a solution to the hierarchy problem that originally motivated its development. However, the improved unification provided by supersymmetry remains a compelling theoretical argument for its existence, even if the particles lie beyond current experimental reach. The Higgs discovery plays a crucial role in these unification scenarios because the measured Higgs mass of 125 giga-electron volts falls within the range predicted by many supersymmetric models, while providing constraints on the supersymmetric parameter space through its coupling to hypothetical supersymmetric particles. String theory represents the most ambitious attempt to unify all 4 fundamental forces, including gravity within a single theoretical framework that treats particles as different vibrational modes of one-dimensional strings propagating in higher dimensional spacetime. The Higgs field emerges naturally in many string models as a consequence of compactifying the extra spatial dimensions down to the 3 dimensions we observe, with the vacuum expectation value determined by the geometry and topology of the compactified space. Different compactification schemes produce different particle spectra and coupling constants, potentially explaining why our universe exhibits the particular values of fundamental parameters that permit the existence of atoms, molecules, and complex structures. The landscape of possible string vacua contains an enormous number of metastable configurations, each corresponding to a different set of physical laws and constants, raising questions about whether our observed physics represents a unique solution or merely one possibility among countless alternatives. The multiverse implications of string theory connect to anthropic reasoning that suggests conscious observers can only exist in regions of the cosmic landscape where the fundamental constants permit the formation of stars, planets, and biological process. Recent developments in quantum gravity and holographic dualities suggest that space-time itself might be an emergent phenomenon arising from more fundamental quantum information structures, with the Higgs field and other standard model fields representing effective descriptions that apply only at energy scales well below the Planck scale, where quantum gravitational effects become dominant. These approaches attempt to derive the standard model from first principles based on quantum mechanical principles and general covariance, potentially explaining why the Higgs mechanism operates as observed while connecting particle physics to cosmology and black hole thermodynamics. The success of electroweak unification therefore provides both validation of the unification program and motivation for pushing toward even more comprehensive theories that might ultimately explain why the universe contains the particular collection of particles and forces we observe, rather than some other combination. Experimental tests of grand unification and supersymmetry continue through precision measurements of standard model parameters, searches for rare processes like proton decay and flavor-changing neutral currents, and direct production of new particles at high-energy colliders. Future experiments will probe deeper into the energy scales where unification might occur while testing the predictions of specific models through increasingly sensitive measurements of coupling constant running, neutrino masses, and cosmological observables that depend on physics beyond the standard model. What if the discovery that completed our understanding of fundamental physics simultaneously revealed that our entire universe teeters on the brink of catastrophic collapse? The measurement of the Higgs boson mass at precisely 125 giga-electron volts, combined with the top quark mass of 173 giga-electron volts, places our cosmos in a terrifyingly precarious position where quantum tunneling could trigger the destruction of everything that exists through a process called false vacuum decay. Theoretical calculations incorporating these measured values indicate that our current vacuum state, while stable enough to persist for times vastly longer than the current age of the universe, does not represent the absolute minimum energy configuration possible for the Higgs field. Instead, we inhabit a metastable vacuum that could spontaneously tunnel to a lower energy state, creating an expanding bubble of altered physics that would obliterate all matter and rewrite the fundamental laws governing reality. This scenario represents one of the most chilling implications ever derived from particle physics measurements, suggesting that the very discovery confirming our theoretical understanding also unveiled the potential for cosmic annihilation written into the mathematical structure of the standard model itself. The physics underlying vacuum stability depends critically on the shape of the Higgs potential at energy scales far above those directly probed by collider experiments, requiring theoretical extrapolations that incorporate quantum corrections from all standard model particles. The top quark plays a particularly crucial role because its enormous Yukawa coupling introduces large negative contributions to the Higgs potential through quantum loop effects, potentially creating a deeper minimum at field values much larger than the electroweak scale. When physicists calculate how the effective Higgs potential evolves with energy scale using renormalization group equations, they find that the measured top quark mass lies dangerously close to the critical value that separates absolute stability from metastability. If the top quark were just a few giga-electron volts lighter, our vacuum would be absolutely stable against any possible tunneling events. If it were significantly heavier, the potential would develop an unstable region that would have caused immediate vacuum collapse during the high energy conditions existing shortly after the Big Bang. The observed value places us in the narrow intermediate regime, where tunneling remains possible but occurs with vanishingly small probability over cosmological timescales. The mathematical formalism describing false vacuum decay treats the process as quantum tunneling through potential barriers, analogous to radioactive decay but involving field configurations rather than individual particles. When the Higgs field occasionally fluctuates to sufficiently large values through thermal or quantum effects, it might find itself in a region where lower energy configurations become accessible through barrier penetration. Once such tunneling occurs, the field would roll downhill to the true vacuum minimum, releasing enormous amounts of energy while fundamentally altering the masses and interactions of all particles within the expanding region. This bubble of true vacuum would propagate outward at light speed, preceded by a wall of energy density that would incinerate any matter it encountered, while transforming the interior into a realm governed by completely different physical laws. The boundary between our current physics and the altered interior would be impossible to detect until the moment of destruction, because light cannot escape from the approaching wall to provide advance warning. Precision calculations of the vacuum lifetime require incorporating quantum corrections from virtual particle loops that modify the effective potential and tunneling rates in subtle but important ways. The leading contributions come from top quark loops that tend to destabilize the vacuum, W and Z boson loops that provide moderate stabilization, and Higgs self-interactions that could either stabilize or destabilize, depending on the value of the quartic coupling at high energies. Current estimates suggest that the vacuum lifetime exceeds 10 to the 100 years, a number so large that it dwarfs not only the current age of the universe, but even the time required for proton decay and black hole evaporation through Hawking radiation. These calculations carry significant uncertainties because they depend on standard model parameters that are not known with perfect precision and assume that no new physics appears at intermediate energy scales to modify the potential evolution. The discovery of supersymmetric particles, additional Higgs fields, or other beyond standard model phenomena could dramatically alter the stability analysis by introducing new contributions to the effective potential or changing the running of coupling constants in ways that either enhance or reduce the tunneling probability. Cosmological implications of vacuum metastability extend beyond the mere possibility of future collapse to influence our understanding of cosmic inflation and early universe dynamics. If our vacuum is indeed metastable, then cosmic inflation must have ended in a way that prevented tunneling to the true vacuum during the violent phase transitions accompanying reheating and particle production. The fact that we exist at all might therefore require fine-tuning of inflationary parameters or anthropic selection effects that favour regions where vacuum decay did not occur during the early universe. Some theoretical models propose that eternal inflation continuously creates new regions of space where different vacuum configurations become realised, with conscious observers naturally finding themselves in metastable regions that permit long-lived structures and biological evolution. Alternative scenarios suggest that quantum gravitational effects near the Planck scale might stabilize the electroweak vacuum through mechanisms not captured by standard model calculations, or that the apparent metastability results from incomplete understanding of higher-order corrections that become important at extreme field values. Experimental efforts to refine vacuum stability predictions focus on measuring standard model parameters with increasing precision, while searching for new physics that might alter the theoretical framework underlying these calculations. Why does the existence of complex chemistry, stable atoms, and ultimately life itself depend on the Higgs field maintaining an energy density that falls within an almost impossibly narrow range among infinite possibilities? The measured vacuum expectation value of 246 giga-electron-volts represents a cosmic coincidence so extraordinary that even modest changes in either direction would render our universe completely sterile, devoid of the intricate structures that make consciousness and biological complexity possible. If the Higgs field had settled at a significantly higher energy density during the primordial phase transition, all fundamental particles would have acquired enormous masses that would prevent the delicate balance of forces necessary for atomic binding and molecular formation. Electrons with masses hundreds of times larger than observed would create atoms smaller than current atomic nuclei, bringing electrons so close to protons that electromagnetic attraction would overwhelm the quantum mechanical effects that normally prevent gravitational collapse of matter into dense, chemically inert configurations. The strong nuclear force would bind quarks into exotic hadrons with masses reaching thousands of giga-electron-volts, making ordinary protons and neutrons impossible, while creating nuclear matter so dense that gravitational effects would dominate over electromagnetic interactions even at microscopic scales. Chemical bonds would become impossible because the energy scales governing electromagnetic interactions between atoms would be completely overwhelmed by the rest masses of the constituent particles, preventing the formation of molecules, crystals, and all the complex structures that emerge from atomic interactions in our current universe. Conversely, if the Higgs field had chosen a much smaller vacuum expectation value, particles would remain nearly massless and travel at speeds approaching light velocity, making bound systems impossible to form because gravitational and electromagnetic attractions would be too weak to overcome the kinetic energies of fast-moving particles. Stars would never ignite nuclear fusion because the weak nuclear force responsible for converting protons into neutrons during hydrogen burning depends critically on the W and Z boson masses, which scale directly with the Higgs field strength. Without massive weak-gauge bosons, stellar cores would lack the mechanism needed to initiate and sustain the fusion reactions that power main-sequence stars and synthesize the heavy elements essential for rocky planet formation and biological chemistry. Nuclear synthesis during the Big Bang would also fail to produce the observed abundances of light elements, because weak interaction rates during the first few minutes of cosmic evolution depend on precisely measured values of gauge boson masses that emerge from the Higgs mechanism. The anthropic window permitting complex structures extends beyond nuclear physics to encompass the electromagnetic fine structure, constant, and other dimensionless parameters whose values appear remarkably well tuned for the emergence of complexity. The electron-to-proton mass ratio, determined partly by Higgs interactions and partly by quantum chromodynamics, must fall within a narrow range that allows atoms to have sizes large enough for chemical diversity while remaining small enough for molecular stability under thermal conditions existing on planetary surfaces. If electrons were much lighter relative to protons, atoms would be enormous and chemically inert, while if they were much heavier, atomic radii would shrink, until electromagnetic forces dominated thermal energies at all reasonable temperatures. The carbon-nitrogen-oxygen burning cycles that enable stellar nucleosynthesis and create the chemical elements heavier than helium also depend sensitively on nuclear binding energies that reflect the interplay between strong force effects and electromagnetic interactions governed by particle masses. The discovery of the Higgs mechanism simultaneously explains and deepens this apparent fine-tuning by revealing that all these crucial parameters emerge from a single underlying field configuration that could have taken any value during the primordial symmetry-breaking transition. The arbitrariness of the vacuum selection process makes the life-permitting character of our universe appear even more remarkable, because no physical principle required the Higgs field to choose the particular value that enables atomic chemistry and stellar evolution. Alternative scenarios involving multiple Higgs fields or more complex symmetry-breaking patterns might naturally produce the observed fine-tuning through dynamical mechanisms that drive the fields toward configurations favoring complexity. But such models require additional theoretical assumptions that cannot be tested with current experimental capabilities. Multiverse theories propose that eternal cosmic inflation creates infinite regions where different vacuum configurations become realized, with conscious observers naturally finding themselves in the rare regions where the fundamental constants permit their existence. This anthropic explanation transforms the apparent fine-tuning from a puzzle requiring special mechanisms into an inevitable consequence of observer selection effects operating across an infinite ensemble of possible universes. However, anthropic reasoning raises its own philosophical questions about the nature of scientific explanation and whether invoking unobservable parallel universes represents legitimate theoretical physics or merely an elaborate way of avoiding the fine-tuning problem without truly solving it. Precision measurements of standard model parameters continue to test whether the apparent anthropic balance reflects genuine fine-tuning, or whether deeper theoretical principles might explain why the fundamental constants take their observed values. Future experiments will determine Higgs and top quark masses with unprecedented accuracy while searching for additional fields or interactions that might provide natural explanations for the parameter values that make complex chemistry possible. The relationship between vacuum stability and anthropic selection also depends on whether our current vacuum represents a temporary metastable state that could eventually decay to configurations with different physical laws, potentially resolving the fine-tuning problem by demonstrating that only certain parameter ranges allow long-term vacuum stability compatible with the existence of complex structures and conscious observers. How did a field that determines particle masses in today's universe also orchestrate the most dramatic transformations in cosmic history, from the initial moments of creation to the ultimate destiny of all matter and energy? The Higgs field's influence extends far beyond its role in contemporary particle physics to encompass fundamental processes that shape the early universe and continue to govern cosmic evolution on the largest observable scales. During cosmic inflation, the exponential expansion that stretched quantum fluctuations into the seeds of galactic structure, scalar fields similar to the Higgs played crucial roles in driving the accelerated expansion, while generating the primordial density perturbations visible today in the cosmic microwave background radiation. Although the inflaton field responsible for inflation remains hypothetical and distinct from the standard model Higgs, both represent scalar fields with similar mathematical properties and dynamics, suggesting that the Higgs discovery validates the theoretical framework underlying inflationary cosmology. Some models propose direct connections between the Higgs field and inflation through non-minimal couplings to gravity that could allow the same field to drive both cosmic acceleration and particle mass generation at different epochs in cosmic history. These scenarios require the Higgs potential to have additional structure beyond the simple Mexican hat form observed at low energies, potentially including flat regions at large field values that could sustain slow-roll inflation before the field eventually settled into its current vacuum state. The transition from inflation to radiation domination involves violent processes called preheating and reheating that convert the inflaton's energy into standard model particles, creating the hot, dense conditions needed for Big Bang nucleosynthesis and structure formation. Baryogenesis, the process that created the observed excess of matter over antimatter, represents another cosmic mystery, where Higgs physics might provide essential insights through mechanisms that violate the fundamental symmetries protecting matter-antimatter balance. The standard model contains insufficient charge parity violation to explain why our universe consists almost entirely of matter, despite theoretical expectations that equal amounts of particles and antiparticles should have been produced during the Big Bang. Extensions of the Higgs sector involving multiple scalar fields with complex vacuum expectation values could provide additional sources of symmetry violation during the electroweak phase transition, potentially generating the matter-antimatter asymmetry through processes called electroweak baryogenesis. These mechanisms require the electroweak transition to proceed as a first-order phase transition with bubble nucleation, rather than the smooth crossover predicted by standard model calculations, necessitating new physics beyond the minimal Higgs sector to strengthen the transition and create the out-of-equilibrium conditions needed for successful baryogenesis. Alternative approaches invoke grand unified theories or leptogenesis scenarios, where heavy right-handed neutrinos decay asymmetrically to create matter. Antimatter imbalances that get converted to baryon asymmetry through Sphaleron processes operating at high temperatures. Evidence for these early universe processes comes primarily from precision measurements of the cosmic microwave background that preserve information about conditions existing roughly 380,000 years after the Big Bang, when photons last scattered from matter before travelling freely through space. The temperature fluctuations mapped by satellites like WMAP and Planck reflect density variations that originated as quantum fluctuations during the inflation and evolved through gravitational instability during the radiation and matter-dominated eras. The statistical properties of these fluctuations depend sensitively on the physics operating during inflation and reheating, including the masses and interactions of scalar fields that might be related to the Higgs mechanism. Measurements of polarization patterns in the cosmic microwave background also constrain inflationary models and could eventually reveal the energy scale of inflation through detection of primordial gravitational waves that would appear as characteristic curl patterns in the polarization data. The ultimate fate of our universe depends critically on the long-term behavior of the Higgs field and whether our current vacuum state represents a stable or metastable configuration that could eventually decay through quantum tunneling effects. Current calculations suggest that our vacuum has a finite lifetime determined by the measured masses of the Higgs and top quark, though this lifetime vastly exceeds all other relevant cosmological timescales including proton decay, stellar evolution, and black hole evaporation. If vacuum decay eventually occurs, it would propagate as an expanding bubble of true vacuum that would destroy all existing structures while establishing new physics governed by different fundamental constants and particle masses. The approach of such a bubble would be undetectable until the moment of impact because information cannot travel faster than light, meaning the destruction would arrive simultaneously with any possible warning signal. Dark energy, the mysterious component driving current cosmic acceleration, might also connect to Higgs physics through vacuum energy contributions or dynamical scalar field models that exhibit similar properties to the Higgs mechanism. The cosmological constant problem arises because quantum field theory predicts enormous vacuum energy densities that would cause much more rapid cosmic acceleration than observed, suggesting that some unknown mechanism cancels most of the vacuum energy while leaving behind the tiny remainder responsible for dark energy. Proposed solutions invoke supersymmetry, extra dimensions, or anthropic selection effects operating in multiverse scenarios where different regions experience varying amounts of vacuum energy. Future cosmological observations will test these connections between particle physics and cosmic evolution through increasingly precise measurements of dark energy properties, primordial gravitational waves, and other signatures of early universe physics that might reveal the fundamental principles governing scalar field dynamics across all energy scales, from particle masses to cosmic acceleration. What if the greatest scientific discovery of the 21st century simultaneously revealed the profound depths of our ignorance about the fundamental nature of reality? The Higgs boson detection, while completing the Standard Model and validating our understanding of mass generation, exposed gaping holes in our theoretical framework that may require entirely new conceptual foundations to address. Despite decades of theoretical development suggesting that supersymmetry should manifest in Higgs physics through modified coupling strengths and additional scalar particles, the measured properties of the Higgs boson show no deviations from Standard Model predictions that would indicate supersymmetric partners lurking just beyond current experimental reach. The Higgs mass of 125 giga-electron-volts, its production cross-sections, decay branching ratios, and coupling patterns all align precisely with the minimal Standard Model without requiring any of the additional structure that supersymmetric theories predict. This absence of supersymmetric signals represents more than just a negative result. It challenges the theoretical motivations that made supersymmetry appear inevitable to generations of particle physicists who viewed it as the natural solution to multiple problems plaguing the Standard Model. The hierarchy problem, which asks why the Higgs mass remains relatively light when quantum corrections should drive it toward the Planck scale, comes even more puzzling in the absence of supersymmetric cancellations that were supposed to stabilize scalar masses against radiative corrections. Without supersymmetry or other new physics, maintaining the observed Higgs mass requires fine-tuning of parameters to 1 part in 10 to the 16, a level of precision that seems to violate principles of naturalness that have guided theoretical physics for decades. The dark matter mystery represents another area where the Higgs discovery failed to provide expected insights, revealing no obvious connections between the mass generation mechanism and the invisible matter that comprises roughly 27% of the cosmic energy density. Many theoretical models proposed that dark matter particles would interact with the Standard Model through the Higgs sector, either as additional scalar particles in extended Higgs models or as weakly interacting massive particles that acquire their masses through new Yukawa couplings to Higgs-like fields. However, precision measurements of Higgs properties show no evidence for such connections, while direct detection experiments have failed to observe the dark matter interactions that would be expected if these particles coupled to the Higgs field with strengths comparable to ordinary matter. The cosmological abundance of dark matter, its clustering properties on galactic scales, and its apparent stability over cosmic timescales all suggest that dark matter physics operates through mechanisms completely independent of the electroweak symmetry breaking that generates ordinary particle masses. This independence deepens rather than resolves the mystery of why the universe contains such different types of matter with completely unrelated origins, masses, and interaction patterns. Perhaps most fundamentally, the Higgs discovery provides no insight into why the vacuum expectation value equals precisely 246 giga-electron-volts, rather than some other value spanning many orders of magnitude. This parameter determines not only the overall scale of particle masses, but also the relative strengths of electromagnetic and weak interactions through the Weinberg angle. Yet no theoretical principle explains why nature chose this particular configuration from the infinite possibilities available during the primordial phase transition. String theory attempts to address this question by proposing that different compactifications of extra dimensions produce different vacuum expectation values, but the resulting landscape of possibilities contains so many metastable configurations that specific predictions become impossible without additional selection principles that remain unknown. Anthropic reasoning suggests that conscious observers can only exist in regions where the vacuum expectation value permits stable atoms and nuclear burning, but this explanation merely pushes the mystery to a higher level by requiring either fine-tuning of initial conditions or acceptance of unobservable parallel universes with different physical laws. The mathematical structure underlying the Higgs mechanism itself raises questions that the discovery cannot answer about why scalar fields exist at all and why they exhibit the particular potential forms that enable spontaneous symmetry breaking. Most known fundamental fields are either fermions that make up matter, or gauge fields that mediate forces, while scalar fields like the Higgs represent a unique category with no obvious theoretical necessity beyond their required role in mass generation. The Mexican hat potential that drives electroweak symmetry breaking could have countless alternative forms that would produce different patterns of particle masses and force strengths, yet the observed potential has exactly the shape needed to generate the standard model particle spectrum without any deeper explanation for why this configuration was selected. Quantum field theory itself provides no guidance about why nature chose scalar fields over alternative mechanisms for breaking gauge symmetries or generating particle masses through dynamical processes that might emerge from more fundamental physics. Additional puzzles emerge from the apparent connections between the Higgs sector and other unsolved problems in cosmology and astrophysics, including the accelerating cosmic expansion driven by dark energy and the matter-antimatter asymmetry that allowed complex structures to form after the Big Bang. The vacuum energy associated with the Higgs field contributes to the cosmological constant in ways that should produce observable effects on cosmic expansion rates, yet the predicted contributions exceed observed dark energy densities by enormous factors that require unknown cancellation mechanisms. The electroweak phase transition should have created conditions favourable for generating matter-antimatter asymmetries through charge parity violating processes, yet the standard model contains insufficient violation to explain the observed asymmetry without additional sources that remain hypothetical. These connections suggest that understanding the Higgs mechanism fully will require solving problems that extend far beyond particle physics into cosmology and fundamental physics, potentially demanding revolutionary changes in our understanding of space-time, quantum mechanics, and the nature of physical law itself. How will the next generation of experiments push our understanding of the Higgs mechanism into uncharted territory, where even the smallest deviations could signal revolutionary discoveries about the fundamental nature of reality? The High Luminosity Large Hadron Collider represents humanity's most ambitious attempt to probe the deepest layers of Higgs physics through precision measurements that will accumulate datasets roughly 10 times larger than those used for the original discovery, while implementing advanced detector technologies designed to extract maximum information from each collision event. This upgraded facility will enable measurements of Higgs self-interactions for the first time, probing whether the scalar field exhibits the quartic and cubic couplings predicted by the standard model, or whether deviations might indicate additional structure in the potential that could explain dark matter, vacuum stability, or other fundamental puzzles. The trilinear Higgs coupling, which determines how strongly the field interacts with itself, directly reflects the shape of the Mexican hat potential and provides crucial tests of whether spontaneous symmetry breaking operates exactly as theorists proposed in the 1960s. Measuring this parameter requires detecting extremely rare processes where two Higgs bosons are produced simultaneously in the same collision, either through direct pair production or through cascade decays involving intermediate particles that subsequently decay into multiple Higgs states. These double Higgs production events occur roughly once in every 100 million collisions, making their observation a supreme challenge that demands both enormous statistics and sophisticated analysis techniques to separate signal events from overwhelming backgrounds of ordinary particle production. The measurement of Higgs self-interactions connects directly to questions about vacuum stability and the ultimate fate of our universe, because the strength of these couplings determines whether our current vacuum state represents an absolute minimum or merely a metastable configuration that could eventually decay through quantum tunneling effects. Precision studies of rare decay channels will test whether the Higgs boson couples to all standard model particles exactly as predicted, or whether subtle anomalies might reveal the influence of new physics operating at energy scales beyond direct experimental access. The decay to muon pairs, predicted to occur with a branching fraction of only 0.02%, lies barely within reach of high luminosity LHC sensitivity and would provide the first direct measurement of second-generation fermion couplings, while testing lepton universality principles that underlie the standard model's flavor structure. Charm quark couplings represent an even greater experimental challenge, because these particles are produced copiously through strong interactions, creating enormous backgrounds that must be overcome through advanced machine learning algorithms and innovative analysis strategies. Future electron-positron colliders like the proposed International Linear Collider or Compact Linear Collider would operate in much cleaner environments where precision Higgs measurements could reach unprecedented levels of accuracy, while studying phenomena that remain inaccessible at hadron colliders. The Higgs-Strahlung process, where Higgs bosons are produced in association with Z bosons, allows model-independent measurements of coupling strengths because the Z boson can be reconstructed precisely while the Higgs decays are studied independently. Threshold scans near the Higgs production threshold could determine the particle's mass and width with extraordinary precision, while revealing subtle effects from virtual particles or modified dispersion relations that might arise from quantum gravity or extra-dimensional physics. Circular electron-positron colliders operating as Higgs factories would accumulate millions of clean Higgs events, while providing access to rare decay modes and precision measurements of coupling ratios that could reveal patterns pointing toward grand unified theories or other extensions of the Standard Model. Gravitational wave astronomy offers unexpected opportunities to study Higgs physics through observations of phase transitions that might have occurred during cosmic history if extended scalar sectors underwent first-order transitions in the early universe. The detection of stochastic gravitational wave backgrounds from cosmological phase transitions could provide information about additional Higgs fields that remain hidden from particle accelerator experiments while connecting laboratory measurements to cosmological phenomena operating on vastly different scales. Advanced detector technologies, including quantum sensors and precision interferometry, might eventually detect signatures of modified space-time structure arising from non-minimal couplings between scalar fields and gravity that could explain dark energy or other cosmological mysteries. The integration of artificial intelligence and machine learning techniques into experimental analysis promises to extract previously inaccessible information from collision data through pattern recognition algorithms that can identify subtle correlations indicative of new physics beyond human analytical capabilities. Each new measurement in the ongoing experimental program tests specific predictions of the Standard Model while searching for deviations that could point towards supersymmetry, extra dimensions, composite models, or entirely unexpected phenomena that would revolutionize our understanding of fundamental physics. The combination of increased collision rates, improved detector performance, and sophisticated analysis methods ensures that Higgs physics will remain at the forefront of experimental particle physics for decades to come, offering the best prospects for discovering new particles, interactions, or symmetries that extend beyond our current theoretical framework into realms where the deepest secrets of nature await revelation. What single moment in scientific history transformed our understanding of reality from theoretical speculation into experimental certainty, while simultaneously opening entirely new frontiers of inquiry that will define physics for generations to come? July 4th, 2012 represents a watershed moment that divided the history of fundamental physics into distinct epochs, marking the transition from an era where the deepest principles governing mass and matter remained unproven hypotheses to a new age, where these mechanisms became established facts that form the foundation for exploring even more profound mysteries about the nature of existence. Before that historic announcement at CERN, the Standard Model existed as an extraordinarily successful theoretical framework that made precise predictions about particle interactions and fundamental forces, yet it remained incomplete without experimental confirmation of its most crucial component, the mechanism responsible for generating mass itself. The theoretical edifice built over decades by brilliant minds like Higgs, Weinberg and Glaujo resembled a magnificent cathedral with a missing keystone, mathematically elegant and empirically successful in its tested domains, but fundamentally uncertain about its most essential assumptions regarding how particles acquire their inertial properties through interactions with an omnipresent background field. Physicists worked within this framework while harboring deep uncertainties about whether the Higgs field actually existed, or whether nature employed some entirely different mechanism for breaking electroweak symmetry and generating particle masses. The absence of experimental verification meant that alternative theories remained viable, including technicolor models that generated mass through strong dynamics without elementary scalar fields, composite Higgs scenarios where the observed particle emerged as a bound state of more fundamental constituents, and extra-dimensional theories that produced effective mass generation through geometric effects in higher dimensional spacetime. The discovery transformed this landscape of competing possibilities into a confirmed foundation where the basic architecture of mass generation became established scientific fact rather than theoretical conjecture. After July 4th, 2012, physics possessed validated knowledge that empty space contains a structured medium with definite energy density, that particles acquire mass through coupling to this background field, and that the entire framework of spontaneous symmetry breaking operates in nature exactly as mathematical models predicted. This confirmation eliminated classes of alternative theories while establishing the Higgs mechanism as the starting point for all future investigations into fundamental physics, rather than merely one possibility among many. The psychological impact on the scientific community was profound because it validated decades of theoretical development and confirmed that human mathematical reasoning could uncover the hidden mechanisms governing reality's deepest layers. The questions that drive scientific inquiry underwent a fundamental transformation as researchers shifted from asking whether the Higgs field exists to investigating how this mechanism connects to other unsolved problems in physics, including dark matter, vacuum stability, quantum gravity, and cosmic inflation. This evolution from existence proofs to mechanistic understanding reflects the natural progression of scientific knowledge, where confirmed discoveries become platforms for exploring new phenomena, rather than endpoints that close off avenues of investigation. The established reality of the Higgs field enables physicists to formulate precise questions about extensions of the mechanism that might explain neutrino masses through seesaw models, connect to dark matter through additional scalar multiplets, or provide insights into grand unification through running coupling analysis that incorporates measured Higgs parameters. The shift from speculative to empirical also transformed experimental programs as collaborations moved beyond discovery toward precision measurements that test whether the observed Higgs boson behaves exactly as the minimal standard model predicts, or exhibits subtle deviations that might signal new physics beyond the current framework. The discovery's impact extended beyond particle physics to cosmology, condensed matter physics, and fundamental questions about the relationship between mathematics and physical reality, demonstrating that understanding mass generation illuminates phenomena ranging from stellar evolution to vacuum stability to the anthropic fine-tuning that makes complex structures possible in our universe. Educational approaches to teaching fundamental physics also evolved as instructors could present the Higgs mechanism as established scientific fact rather than speculative theory, enabling students to build understanding on solid empirical foundations while appreciating how theoretical insights guide the experimental program that led to confirmation. The technological spillovers from the discovery continue to influence multiple fields as the detector innovations, computational methods, and data analysis techniques developed for Higgs physics find applications in medical imaging, materials science, and artificial intelligence research that extends far beyond the original particle physics context. Perhaps most significantly, the successful completion of the Standard Model provides humanity with its first complete theoretical description of fundamental interactions at the quantum level, representing an intellectual achievement comparable to Newton's laws of motion or Maxwell's equations in establishing mathematical frameworks that accurately capture essential aspects of natural phenomena. This accomplishment demonstrates that human scientific inquiry can penetrate to the deepest accessible layers of physical reality and extract quantitative understanding of mechanisms operating at scales completely removed from direct sensory experience. The validation of such abstract theoretical constructs as quantum fields, gauge symmetries, and spontaneous symmetry breaking reveals something profound about the mathematical structure underlying reality and the remarkable capacity of human reasoning to decode nature's hidden organizational principles through combinations of theoretical insight and experimental verification that bridge the gap between pure mathematics and empirical observation. What if the most profound revelation in physics shows us that everything we consider solid and substantial emerges from invisible interactions within an active, structured void that challenges every intuitive notion about the nature of existence itself? The Higgs discovery fundamentally transformed our understanding of empty space from a passive backdrop, where events occur to an active medium that participates in every physical process, through its omnipresent energy density and field structure that permeates all regions of the universe without exception. This revelation demolishes the classical conception of vacuum as nothingness and replaces it with a dynamic quantum arena where virtual particles continuously fluctuate, fields maintain non-zero values, and the very geometry of space-time responds to energy density in ways that shape the behavior of matter and radiation. The vacuum expectation value of 246 giga-electron volts represents more than just a number. It quantifies the energy content of apparently empty space and demonstrates that regions devoid of particles still contain enormous amounts of structured information that determines how particles will behave when they enter these regions. This understanding connects the microscopic world of quantum field theory to macroscopic phenomena, including stellar evolution, galactic dynamics, and cosmic expansion through mechanisms that operate continuously throughout space and time, regardless of whether matter is present to observe them. The emergence of mass from interaction rather than substance represents perhaps the most counterintuitive insight ever achieved in fundamental physics, overturning millennia of human intuition about what gives objects their weight and resistance to acceleration. Instead of mass being an intrinsic property that particles carry like tiny balls of matter, it emerges dynamically from coupling strengths between particles and the omnipresent Higgs field through processes that occur at every moment and in every location throughout the cosmos. This perspective transforms our understanding of materiality itself because it reveals that the most basic property we associate with physical objects arises from relational processes rather than from substantial essences that exist independently of environmental interactions. Electrons do not contain mass in any literal sense but generate their inertial properties through continuous coupling with the background field, while photons remain massless because they fail to interact with this field under any circumstances. The implications extend beyond particle physics to questions about the nature of information, consciousness, and biological processes that depend on precisely the mass relationships generated by Higgs interactions. Spontaneous symmetry breaking operates as a fundamental organizational principle that shapes reality at every scale from subatomic particles to cosmic structures, demonstrating that nature consistently chooses asymmetric configurations even when the underlying laws remain perfectly symmetric. This principle explains not only why electromagnetic and weak forces appear different, despite arising from the same unified interaction, but also why complex structures can emerge from simple initial conditions through phase transitions that amplify small fluctuations into macroscopic patterns. The Mexican hat potential that drives electroweak symmetry breaking exemplifies how symmetric mathematical structures can produce asymmetric physical outcomes through instabilities that force systems away from high symmetry configurations toward lower symmetry states that become the foundation for all subsequent evolution. This mechanism appears throughout nature in phenomena ranging from crystal formation and magnetic ordering to biological pattern formation and social organization, suggesting that symmetry breaking represents a universal principle governing how complexity emerges from simplicity across multiple domains of existence. The cosmological implications become profound when we recognize that the particular symmetry breaking pattern realized in our universe determines not only particle masses and force strengths, but also the fundamental constants that make chemistry, nuclear physics, and biological evolution possible. Understanding these mechanisms illuminates deep questions about consciousness and life by revealing how the information processing capabilities that underlie cognition depend on precisely the particle interactions and field dynamics established by Higgs physics during the primordial phase transition. The stable atomic structures that enable complex chemistry require specific mass ratios between electrons and nucleons that emerge from the interplay between Higgs-generated fermion masses and quantum chromodynamics binding energies that together create the delicate balance necessary for molecular diversity. Neural processes in biological systems operate through electrochemical gradients that depend on ion masses and electromagnetic interactions governed by parameters fixed during electroweak symmetry breaking, connecting the deepest principles of fundamental physics to the emergence of information processing and conscious experience. The philosophical implications challenge materialist assumptions about the relationship between mind and matter by suggesting that consciousness might emerge from informational processes operating within the same field-theoretic framework that generates mass and determines particle interactions. If mental phenomena arise from patterns of activity in neural networks whose basic operations depend on field interactions and symmetry principles rather than on classical mechanical properties of material substances, then understanding consciousness might require insights from quantum field theory and symmetry breaking mechanisms that operate at scales far removed from direct neurobiological observation. The discovery that empty space has structure and that mass emerges from interaction rather than substance opens new perspectives on fundamental questions about why anything exists rather than nothing. why the universe exhibits the particular organizational principles we observe, and how conscious beings capable of understanding these principles could emerge from physical processes governed by mathematical relationships that seem perfectly adapted for generating complexity and enabling self-awareness. Why does a subatomic particle that exists for less than a trillionth of a second hold the key to understanding the most enduring questions about existence, purpose, and the ultimate nature of reality itself? The Higgs boson's ephemeral lifetime of approximately 10 to the minus 22 seconds represents one of the briefest measurable intervals in physics, yet this fleeting existence reveals truths about the universe that have persisted since the first moments after the Big Bang and will continue to shape cosmic evolution until the end of time. This paradox between temporal brevity and eternal significance illuminates how quantum field theory operates through principles that transcend individual particle lifetimes to establish the permanent background conditions that govern all physical processes throughout space and time. The field that gives rise to these transient particles maintains its non-zero vacuum expectation value constantly across all regions of the observable universe, creating the stable foundation upon which chemistry, nuclear physics, stellar evolution, and biological complexity depend for their continued operation. Understanding this connection between ephemeral quantum excitations and enduring cosmic structures reveals that the most fundamental aspects of reality operate through mechanisms that exist primarily as potentiality rather than as manifest phenomena, suggesting that the deepest truths about nature concern not what we observe directly, but the invisible principles that determine what can possibly be observed. The relationship between microscopic quantum fields and cosmic evolution demonstrates that the universe exhibits a hierarchical organization where processes operating at the smallest conceivable scales determine the character of structures spanning billions of light years and evolving over cosmic timescales that dwarf human history. The vacuum expectation value established during the electro-weak phase transition, approximately 1 picosecond after the Big Bang, continues to influence stellar nucleosynthesis rates in contemporary stars, galactic formation processes that operate over hundreds of millions of years, and the long-term stability of matter itself across timescales that exceed the current age of the universe by many orders of magnitude. This cascade of influence from quantum to cosmic scales reveals that understanding particle physics provides insights into phenomena ranging from the formation of the first chemical elements during Big Bang nucleosynthesis to the ultimate fate of black holes through Hawking evaporation processes that will continue long after all stars have exhausted their nuclear fuel. The mathematical frameworks developed to describe Higgs physics apply equally to cosmological inflation, dark energy dynamics, and other large-scale phenomena that shape cosmic evolution, demonstrating that the same theoretical tools illuminate both the smallest and largest observable structures in nature. The question of why anything exists rather than nothing becomes more tractable when we recognize that the universe chose to break its own fundamental symmetries during the earliest moments of cosmic history, transforming a perfectly symmetric but unstable configuration into an asymmetric but stable state that permits the existence of complex structures and conscious observers. This symmetry breaking represents more than just a physical process. It embodies a principle of cosmic creativity where potential becomes actualized through spontaneous transitions that could not be predicted from initial conditions alone. The fact that our universe selected one particular vacuum state from infinite possibilities during the primordial phase transition suggests that existence itself involves irreducible elements of contingency and choice that cannot be eliminated through more complete physical theories or deeper mathematical understanding. The philosophical implications challenge both purely materialist and purely idealist approaches to understanding consciousness and cosmic purpose by revealing that reality emerges from interaction between mathematical structures and physical processes that neither reduces to pure computation nor requires non-physical intervention to generate novelty and complexity. Understanding mass generation helps illuminate why anything exists by showing that the most basic properties of matter arise from dynamic interactions rather than from static essences, suggesting that existence itself might be fundamentally relational rather than substantial. The discovery that mass emerges from coupling strength rather than intrinsic substance implies that the universe operates through principles of relationship and interaction at its most fundamental level, potentially offering insights into how consciousness and meaning might emerge from physical processes without requiring violations of natural law or appeals to supernatural intervention. The anthropic fine-tuning evident in the precise values of coupling constants and vacuum expectation values that make complex chemistry and biological evolution possible connects to deep questions about whether conscious observers represent inevitable outcomes of cosmic evolution or extraordinary accidents that reveal something profound about the relationship between mind and matter. The fact that we live in a universe capable of understanding its own organizational principles through scientific inquiry suggests either remarkable cosmic coincidences or fundamental connections between the mathematical structures that govern physical processes and the cognitive capabilities that enable conscious beings to comprehend these structures. The philosophical significance of spontaneous symmetry breaking extends beyond its role in particle physics to encompass questions about creativity, novelty, and purpose in cosmic evolution, revealing that the universe exhibits genuine historical development rather than merely rearranging predetermined elements according to eternal laws. This perspective suggests that scientific understanding of fundamental physics provides insights not only into how the universe operates, but also into why it exhibits the particular creative potentials that have generated stars, planets, life, and consciousness through evolutionary processes that continue to unfold in directions that cannot be predicted with certainty from current knowledge. The cosmic significance of the Higgs discovery therefore encompasses both its immediate implications for particle physics and its broader relevance to understanding existence, consciousness, and meaning in a universe that demonstrates both mathematical elegance and creative spontaneity at its deepest accessible levels. Tonight, we've traced how finding a single particle revealed the hidden architecture of existence itself, from the moment empty space gained weight to the realization that our universe chose to break its own symmetry. The Higgs discovery didn't just complete our understanding of mass, it opened doorways to mysteries that will guide physics for generations. If this journey through the deepest truths about reality brought you a moment of wonder, your support means everything. A gentle like or subscribe helps these explorations reach others who share our fascination with the profound secrets waiting in the quantum realm.